Okay, I will share my screen also. Let's start with this one. Is this one clear to all of you? By the way, if anything is, I mean, like in the Zoom control, you have that thumbs up symbol, or you can just unmute and tell me also.
Yeah.
Uh,
This I got. I think I believe I understood the basic, like, yeah, the concept.
okay, what about fathers?
I think, again, if it'd be better if you could explain.
Yeah, okay. So it's like this. It's like a it's averaging image. So you can see this is the same image, same place, but this person is moving. The whole intention is when we take these first 15 images, there are 15 images, then we can recreate this last image. There is no human on that. There is no like disturbance. For example, if it is a street, like all these vehicles are moving. So we cannot take an image of empty roads. So what we can do is we can take multiple images, and when we combine them, so magically this all the vehicles and all the things, it disappears. So how it is happening? Like let's say for example, on a given point, let's say this point, all these images on this point, you can see it has some white background, but when the human enters that point, only this point it becomes darker, because all other points it's like white. So the pixel value, it's always from 0 to 255. There are two scales of pixel value. Either we will keep it in 0 to 255, 0 to 255 in JPEG images. In the other scale is we will keep the values between 0 and 1, like in decimal numbers. This is how we keep it. But let's say, for example, in here, the color value is like 200. So only one point, this value is manipulated. So what we can do is we can open Excel. So let's say the value is 200. And we have 15 images. So on that particular pixel, it's repeated on 15 images, but only one place, which image? It is this one. This is the seventh one. Seventh one, directly this human is on top of that. Seventh one, the value is lower. So let's say the value is like 30. Yeah. But when we average this, I take the sum of this and divide by 50. You can still see it's a high value, like it's almost same to 200. So when you average it, so like it's like if you increase this count number of images, it is far more better. But even with this, you can see this is, I mean, you can barely see a difference. In here, the last image, you can, when I zoom it, you cannot see much difference, but it's a little bit darker. But you cannot see because in this image also it's darker. So when you average this, so all the distortions, it's get disappeared. So this is the purpose of this. Is it understood? Maybe.
Yeah. Yes.
Yeah. I think it is pretty
Okay.
much okay. Yeah.
Lisa, Sonu, Asha, you guys also need to unmute and just tell like it's like a discussion.
Yes, I understood again.
Yes, got it.
Okay. So this is exactly the same thing he explained. Because the first part, it is not much relevant to what he's teaching now. So I will move that part very fast. Whatever the important thing I will just mention. Yeah. Then the second thing, the first actually what he did was, we compare the images with norm. Then only we went into the Hilbert space. So in the norm, there's one formula. This is the formula. This value always should be lesser than 1. So if the image is similar, like if I compare two exact same images, I should get the value 1. So this is to the Q value. This Q value is to see how similar these images are. So what we can do is, I mean, there's one more concept. Even though the image is darker or lighter, it says you will get the same value. There is no difference. So what we can do is we can run a small Python program for this. So this is the yeah, I imported a couple of faces. Then I extracted the same person's like red, and I'm comparing this red channel with the green channel. You know, this images has like 3 dimensions. So it's like this. If you take image, all the values are stored in array. So every position you have the values between 0 to 255. But likewise, you have another array behind that and another array behind that. Each represent for different colors. First one is for R, second one is for green, and third one is for blue. This is the exact same thing I did in here. The RGB 3 channels, so I extracted and I printed. And this is an image with 3 layers, but except the first layer, I made everything into 0. Except the second layer, all other layers I made it 0. So basically, it's showing only the red channel, green channel, blue channel. Then, by the way, this is one more thing. When you compute a norm, let's say norm of A, you get a single value. But scalar product, you will get a matrix. So always in here, it's a single value. But also for the input, you cannot give 2 values. You need to give 1 value. Just remember that point. Yeah. Okay. So in here, when we compute this q value is nothing but, you can see the equation itself. First, 2 images, we need to add them together. Then we need to pass in here. We need to calculate the norm. But before calculating the norm, we need to add them together. Let's say, for example, if we take 2 images, A1 equal to something like some vector like it has 2 points, 2 pixel image, 1 and 1. And A2 is equal to 2 and 2. So the first part, A1 plus A2 norm, what you need to do is you need to add them together, then only you need to pass into here. So you cannot pass them and add it. So first you need to calculate A1 plus A2, that is equal to 3 plus 3. And when you take the L2 norm, it's same like Euclidean distance. So you take the first one square and the second one square, you get 9 and 9, 18 square root. And for this one, A1, it's like 1 square plus 1 square, that's mean square root of 2. And the A2, this is A1, that is 2 square plus 2 square.
Here.
Yeah. So what we are doing is basically Q. I will write it in here. Our Q is equal 18 square root divided by 2 square plus 8 square. This is how the calculation is done. Let's say if it is images, A1 is an image. So it's nothing but it has many values. There is no difference. It has many values. That's it. So exactly the same calculation. Just for fun, what we can do is we can do one thing. Let's say if the images are same, A1 is 1 and 1, and A2 also, we can put 1 and 1. No, we'll put 2 and 2. It will be easy for us. So A1 also, A2 also 2 and 2. So when we add this into Q function, first we need to add them together and add it. So it's like A1 plus A2 equal 4 and 4. Okay. So the above part, it comes square root of 4 square plus 4 square. Down part, it comes 2 square plus 2 square root 2 square plus 2 square. The above part, it comes 1632 square root. This is square root of 8 and 8. Am I right?
Yes.
Yeah. So we'll do the calculation also. I thought we'll get some good numbers, but unfortunately no. So we get 5.65 in the above. Square root of 32. 5.65. Down part we'll see. We got square root of 8. 2.28. That's 2.82. And 2 of them. So we need to multiply them by 2. So we get 5.65. 5.65. So the answer is 1. So this says this value should be always lesser than 1. If the images are same, if the A1 and A2, the comparing images are same, you get the value is 1. If that's minor modification or something, always the value is lesser than that. So we just compare 2 pixel image. So now we'll try to compare a big image. This is the same thing I did in the Python program. So in here, I'm comparing the red face and the green face. You can see this is like the same person, but you can see the mouth and nose, it appears in different ways. It's not exactly the same, but it's the same person. It's like somewhat similar, like something like in 90% similar images. So I can show you. This is the green face. This is, I believe, the red face. This is how the, if I just print only red, because in the Python, if you take the first one, it will always come with green. But actually speaking, 0 in the sense, like is this part understood? Like, RGB, we have 3 arrays. Is that understood for everybody? Or should I explain more?
It's kind of okay.
No, it's understood.
Understood,
Yeah.
right? Okay.
Yeah.
Yeah. So in here, whatever this is R, this is the green, and this is blue. Whatever the thing, I just take it out. In here, I took the zeroth one in the sense, the red face, red array. If I just take it and print it, it comes in green, but it doesn't mean it's green. So that's why in the down, I print it in the proper way in here. So in the red one, you can see face is like this. If I just take the green one, see the face is different, and the blue one, see it's not the same. It's captured different, like the every color, it captures some different brightness and contrast of the face also. So I will compare this one with this one. This is what I'm doing. And here we will compare the red and green. A1 is my red and A2 is my green. So what I will do for here, I will add them together and calculate the norm. And here I will calculate the norm. This is exactly what we did. It's like the Euclidean distance, L2 norm. And when we calculate it, we get a value around 0.71. It's not exactly the 1, it's 0.71. But if I compare the same face, R with R, I should get 1. See, I'm getting 1. But that's the maximum value you get. Always you will get lesser value. Then what I can do is, in here, oh no, this calculation is wrong. I make a comment. Because the thing is, when you add them together, the mistake in here, yeah, I can explain the mistake also. In here, there are three arrays. In the second image also, there are 3 arrays. So when you take the red face, it's in your 0th position. And when you get a green, it's in the first position. And when you take only these 2 and add them together, it will not add, because it's in 2 different levels. This is in the 0th level and this is in 1th level. So you can add them like that. So in the I made one correction in the program. In here, I select the red color and assign into not to 3D one, 3D array, assigning into a 2D array. So only one color will be there, just like a black and white image. In here also red one, I'm taking it and assigning it. Then when I calculate the norm, I get 99% 5. It's the same person, I get 99% 5. But when you compare with a different person, you get like I'm comparing these two faces. Now you can see it's lesser than that. The same person, I get 99.5. And even with the same color, if I check the red, it comes 1. With a different
Yeah.
color. Yeah.
Again, but the image before you said 0.071, right?
No,
That
it's
was
it's no, it's a like the one part is wrong. What is wrong actually? In here it is wrong, because the thing is in here R1 and R2. In here, if you see my R1 and R2 in here, first I create one empty array. This is I can explain you the mistake also. I create one 3D array, empty one with all zeros. Okay, so I made one in here with 3 layers, 3D array, all zeros. Then what I did was for the first one, zeroth one, I assigned the value from my original image. My original image is face image. I assign values to this one. And for the G also, I made the same thing. Sorry, I make it real scale. This is I'm talking about here. I made one with 0, 0, 0. Every place it's 0, 0. Then for the level one, that's been in here, this one, I assign the value from the original image. So I get values assigned into this one. But when I add them together, it will not add, because it's in 2 layers. So my result image, I should not get like 2, 2, 2, 2. It should be the one we are looking for. But what I will get instead of that, I will get in the first layer, I will get 1, 1. Second layer, I will get 1, 1. And third layer, we didn't do anything. It's all zeros, 0, 0, 0. So it's not added together. So it's a mistake. So what I did was in the second program, when you write the programs, actually you are learning this concept. The second concept, I didn't make any 3D arrays. I just made only 2D array. For first image, A1 image, I copied these values, and the A2 image, it's a 2D. I copied these values and add them
So
together.
now this will be kind of grayscale image, right? So if you have three
exactly.
pixels, then only it will be color. Yeah.
Yeah, exactly. Now I made two. I just took only one layer, and it's grayscale image. This is gray. This is gray. And add them together, then you will get 2, 2, 2, 2. Okay. Otherwise, it's a calculation mistake. So now when you add them together, you can add it like this. Now you can calculate the norm. But if you do it like this, it's a wrong calculation. That's why we got 0.71 accuracy. If you do it in the correct way, we got 99. Yeah. And when we compare with a different person, we always get lesser than that. See, 0.94. Yeah. Then we should go to the theory part. So it says even the image is darker or brighter, it doesn't matter. It can still verify the image. So we can do that. So the same red face, I can just multiply with some scalar. So if you multiply with like a small scalar, you will get a dark image. So if I scale with a higher value, you will get a bright image. The original, I mean, if you scale with 1, obviously nothing happens. Like 1.1, you can see it's getting brighter. Like it's like 2, it will be so bright. Yeah. So you got the idea, right? So what we are trying to do is now compare this one with the original image, the red original image. So in here also, I make another black and white grayscale image from the C, the newly constructed image. I will take only one part of that, and in this one also, this is the original one. Nothing has happened for that. This is the original one. When we compare these two, when we can add them together, and calculate the norm. It's the same equation. It's the same equation like here. It's the same equation. So we will add these two together and calculate the norm. Then we will calculate the norm separately and add them. Then we get 99.99. It's almost 1. See, you can see up to 1, 2, 3, 4, 5. 5 decimal point, it's 9. So
Even if we take the whole 3 matrices, that is the actual phase, then also the result will be same. Right?
Yeah, we can try it. We can give it a try.
Hmm.
We'll take the original image. Original image name was, I think, face. Yeah, it's just a face.
Okay.
Yeah, we'll do that. In here, we'll take the image in here and we'll just print it. Yeah, it's a dark face now.
Yeah.
Without doing any filtering. Yeah, I will just come in these 2 lines. So one is C.
And one is phase 1.
Yeah, in here A1, our A1 is now C, and A2 is the original
Phase
image, phase 1. Yeah. So guys, you know what is phase 1 in here, right? So I will just put here phase 1 image, nothing but if you print it, it's this one. So now we are comparing this one with the darker image, these two. When we compare, we still get the same results. So in the image processing, the whole idea is even the image is darker or brighter, it doesn't matter, still we can verify. So it will not impact.
So again, the whole idea about this Q is the Q value will be same if both the images are same.
Yeah, exactly.
If it is 2 different images, then the value goes lower, right?
Yeah. So for example, well, like you are the police and you have a criminal database, lot of photos, and you have the actual criminal. So you can take the photo and just put it in the database and compare. But this is a very, very basic stuff. So like this is not a perfect one, but this is like the ABCD. This is how the concepts start. So that's the main thing. But the main idea, like what Yusuf used to say, the take home message, even the message, I mean, image is darker or brighter, it doesn't matter.
Yeah. Got the point.
Got the point, right? Okay.
Yeah.
Okay. So, but the thing is, this is, yeah. So, but it is not a like perfect calculation. So I compare with this face, the university image. So still I got 9.93. So like we should stop from here on this calculation. So I will go back. The norm, actually, we don't need to spend much time. So we can directly go into different. The main thing is scalar product, the Hilbert space. The Hilbert space, the main thing is the Hilbert space. This property is the main thing. Norm of a vector, it's equal to the inner product. I mean, square root of inner product. So this is the main criteria of the Hilbert space. All other rules are same. But in here, there's one thing, the scalar product, and we used to say scalar product and inner product and dot product. All of them are same in here. So I can explain you. Like everybody, we know what is dot product, right?
Yeah.
Yeah. So, and what is the difference between scalar and dot product? Scalar, what it does? Scalar or inner product. Inner product always check the angle between two vectors. So that's a main idea. I will explain down the line. I will explain it more. But in here, he wrote this one. We check the comparison between these two. In here, if you check this is actually a dot product. So when normally if you write a dot product, it's like this. You have some values, 1, 2, 3, 4, and we have another vector 1, 2, 3, 4. When you calculate the dot product, what happens is this position gets multiplied with this. So 1 multiplied with 1, and this position gets multiplied with this, 2 multiplied with 2, 4, 3 with 3, 3 multiplied by 3, 9, 4 multiplied by 4 here, 16. So we get the sum of that. In here, if you check it, this is the same thing here. You are just incrementing I. So if this is the I position, so if you increment I, first we will pick the 0 position, then we will pick the 1 position, then we will second position. Like that, we are moving the position, right? This is same like dot product. So in the vector space, this is not generally true because in the mathematics, inner product and dot product, it's not the same because the scalar product, it's defined for everything, not only for vector space, but in the vector space, scalar product, dot product, and inner product all are same. So like don't like then the concept becomes very, very easy. So and all of these are same in here. You can see from the here, like he proved it. So even you can calculate this value now. Yeah, but the thing is in here, normally we will not check the, like you can see it's the same thing he's submitting here. I told you like you cannot, for the norm you can submit only one value, but for the inner product or scale product you need to submit two. But in here he compared the same image, angle between same image. So this is not what we need to do, but he just explained it, the concept. Okay. Yeah. So before going further, I will explain you some other. I will explain you this part also. Yeah. First, I will jump into this one and I'll come back. When you compare the angle between images, so it's like it's a varying value. Like it's like, let's say this is the theta angle. So angle between images, in the sense, it will be a like varying value. But what we need to do is we need to align this into a 0 and 1 scale. So there is a mathematical equation. The equation is u dot v equal v cos theta equal, yeah, this is in I believe now for math, now math course also they taught us. So this is the same thing actually. They took this part and put it in down. And the thing is, this value always varying from 0 and 1. And the cos theta, you know the cos values. If you make one graph, cos start from here like this. So cos 0 is 1, cos here 90 is 0, 90 is 0. So when the two images are same in the sense, like first of all, I will explain you what two images are different. The maximum difference what two images can get. You know, this is one image laying on here, and there's another image here, third image here, fourth image here, fifth image here, sixth one like this, 90 degrees. So 90 is the maximum one, because when the image moves here also, you can calculate the angle from other side. So 90 is maximum. Even when your other image falls in here, when you compare the angle between that, you can compare from the other side. So 90 is maximum. So, and when the images are in 90 degrees, we have a special name. It's called orthogonal. So that's the maximum difference that image can get. When the angle is 90, what's the cos theta value? Cos theta value is 0. Yes, cos theta value is 0. So based on this equation, we get 0 if the images are different. But in the other hand, what if the images are same? When your first image is laying in here and second image also laying in here, what's the angle you get? You get 0. Angle is 0. There is no difference in the angle. Then what's the, like from this equation, without doing any part on here, we know based on the cos theta, When the cos 0, what's the value? You get 1. So based on this equation, if the value get 1, that means images are not same. But wait, did I make a mistake? Cos 0. When the images are same, we get value 1. When the cos 90, the orthogonal, we get value 0. Okay? Everybody understood?
Yes.
Is this the same equation like the similar to the one before?
Yeah, it's almost similar, but the thing is, in here we introduce an angle. Previously, we didn't introduce an angle between images, but in here we compute the angle between images because this measurement is better than the previous one, a lot more better than previous one. Previous one we compared actually pixel to pixel value. We didn't compute any angle, but in here we are comparing the angle between images.
Yeah. Okay. Okay.
Yeah. So the best part is in here also I can explain you if the image is brighter and darker. If for one image lying in here and another image lying in here, in the top of that, we get the value angle is 0. That means the output is 1. But let's say another image parallel to this in the sense, parallel to this upside in the sense, alpha we multiplied by 1.2 or something. We made the image brighter. And if it comes from downside, like in here, that means alpha is something like 0.5.
0.5.
Yeah, same image, but we just make it darker or lighter. But these are parallel. So even though those are parallel, like
Well, it is.
Angle will not change.
angle is the same. So you get the same value. So this is the explanation.
But at symmetric positions, you will get the same angle, right?
Like
in the first quadrant and in the second quadrant, we'll get the same. Yeah. Or in third or fifth. Yeah.
Yes. Symmetrical, we can maybe make a program to, make it like change the axes. Then as you said, it should get the same value. I didn't compute it, but we should get the same value.
Maybe, yeah.
Yeah. And one more bit, I'll go back and come. So in here is the second program. I'll run from the beginning. So in here also, it's the same thing, but this program, Yusuf said, like these are used to compute small things. Like we cannot compare two images together. For example, part of the image we can check where it is. For that kind of purpose only we use these programs. So we will not use this to compare whether these two images are same. So, but we will compute this to see what's the matching part for this. Like there's a person, I'm just sending the eye, so I need to pick the point where the eye is.
Even with MATLAB, we did something similar, right? In the lab.
Exactly. So it's like it's the same program where we wrote it in the because in here I wrote two for loops because one is to do the convolution from I'm just moving from here to this direction, then line down also, one for loop to go in this direction, one for loop to go row wise, go down. Yeah.
For each pixel, we need to do like that. Yeah.
Yeah. But in my case, it's not actually a convolution. I'm starting from here inside. But in the convolution, what happens is starting from first pixel like this, then it will move to the second position, and it will move to the third position. Like then when it comes to go down, it will start like this. Sorry, not like this. This is what it first matching position is this 0 and 0 in the first pixel like this. But in my program, it runs like this. So this is not exactly a convolution, but it follow the same way. It goes like here, line by line, it will go. But when I compute these values, this is the I just cut the I into it. This is the upper part. I can see like the up should be somewhere. It's defined in here. Yeah. Inner product of the original image also, I'm just cutting up one piece at a time and comparing it. Yeah. Then the down part, I will calculate the norm of the eye and the cut part, and I will, it's exactly the same formula.
So why did you do 2 times that transpose? Is it something? Okay.
Yeah. See, the thing is,
Okay.
when we usually take these images, the use of how he did it and how I did it, it's a little different. What Yusuf did was, he took this one as 2D. This is 2D.
Okay.
Yeah. In the second array also, he took it as 2D. That's why he used that double sum command and everything.
Yes, double sum. Yeah. Okay.
Yeah. So if you need to, make it same like your book, in the book, this is not for 2D. This is for 1D. Because in the 1D, we can, like, if we have one pixel lines, like comparing everything, like even I told you how the multiplication is happening. Multiplication is happening. You have one pixel line, and second one you need to make it as orthogonal. Then you multiply. But it has only one pixel, no 2 by 2. But the 2 by 2, it's like hard to visualize, right? So what I did was, I took this I and I make it the long vector, long 1D vector.
Rectangle. Yeah.
Yeah. So it's long 1D vector.
Okay.
Yeah.
Okay. So each row after row, you made it.
Yeah. So then I can, exactly like the book, I can put the equation exactly like that. I don't need to do sum and all of these things, because why I don't need sum, and why he needs sum. Okay, in here in the mathematics, like when we compute these two together, dot product, we need to match this side and this side. This is the rule says. But your resulting matrix, you will get this into this. So the result one, you should get 1 by 1 matrix, right?
If it's 1:4 into 4:1, then it will be 1:1.
Exactly. Yeah, exactly. So if it is like 4 1 by 4, like this is called 1 by 4, right? 1 by 4, and this is like 4 by 1. So this here, how many columns into how many rows we need to match it? Then the result is rows into columns. Here it's 1, and here it's 1. You get 1 by 1. So we don't need to do any sum up. We don't need to do a summary. But in his one, we are multiplying.
But he didn't do the transpose, right? So maybe, or all rows into,
Yeah, because the thing is, his program is intelligent enough to do it. It's all happening in the background. But like to get the better understanding, if we implement from the beginning, we know it, right? So that's why when you convert this into one row vector, on this side, no need to do anything. But this side, I need transpose, right? I need to get one column vector. Yeah. So that's why I transpose it. Yeah. So you can see 1D, because I converted into 1D in the program.
I understood.
Yeah.
Now I understood why.
Yeah. That's why I didn't use any summary command, because if we, like, based on this theory, you don't need to compute anything, because if it is in 1D vector, you don't need to take a sum. It gives you one value. This is what in the exam also, last exam also, we got one question like separability. We got one vector like this and another one like this. 4 values. The answer should be in this one 4 by 4 matrix, because you are matching this one into this one, and what you should get this into this. That's mean 4 by 4.
Yeah, this is 4:1, and the other one is 1:4. Okay.
Yeah. So that's why they said this is like the lesson 8 actually. When you I will come back to this again. This filter, like again is called this filter. If it is a filter, we can separate into two 1D filters.
Yeah.
Because when we multiply these two, we can exactly get this. So that's why, like, this is like a separable filter. So I'll come back to that in that part.
Okay.
Yeah. So in here, I will go fast now. When I compare this, when I run the program, yeah. So these are the faces I compare with my original image, original eye from original, I took it from this image actually. Yeah. So yeah, you can see it's a 92% match. No, I'm matching with the second image, phase 2. With the second image, like with the first one, it should get 100% match actually, but I'm not displaying it in here. With the second image, I'm getting 92% match. Then the highest match we get in these two also, 6 and 7 phases. 6 and 7 also, 5, 6 and 7. This is also same, Angelina Rajoli, same person. Yeah, so we got highest matches on second and second, 4, 5, 6 and 7. See, exactly, you can see we got a highest match in here, and we got highest matches in here. So with the same person, it kept, this method we could, use to verify the eye.
Okay.
Yeah, this is a better method. Yeah, got it right.
Yeah.
So yeah, we will go to the next part. So before going to further any detail, yeah, in the lab one also I will just explain something. Then I will come back because we need the lab one to understand. It's a very simple thing, but it has a whole idea what we are doing. Okay. I will just run this program. Part one, I believe. Yeah, exactly this one. So, like everybody understood this program, or shall I explain?
You could just run it through, I think, again.
Yeah, okay. Yeah, okay. So in here, we have pattern. We have small, just like my eye program. This is very simple, basic one. We have our original image. Original image is nothing but in this side it's black and middle part is like low color. It's not exactly white, but we can say it's like a black and white image. And when I apply this filter, in his program, it's applying as convolution. So you will enter into here, and just like my eye program, it will go like this. Every position, every possible position, it will go like this. Then it will go to down like this, here. It will not go to here because it will go every pixel. Like if you check first in this position, second it will actually check in this position, third it will check on this position like this. When it goes down also, it will go down 1 pixel down like this. So when it comes into here like this, so you can see my white side is in here and black side is in other. So this is the most mismatched position, right?
Yeah.
You can see it's like change, like it's totally negative other side. I should get white and black, but in here it's black and white. So that's why it's the highest like mismatch position. I'll make it like full screen. So another part of this program, it will put a black dot if you find the highest mismatch position, and if you find the highest matching position, it will put a white dot. So that's why program itself, they put the black dot. And here, when my filter is in here, left side, it is white, exactly left side in my white, right side, it is black. My right side is black. So this is perfect match. So when the filter comes in here, it's a perfect match. So it identified this is as a matching position. So this is very important. Why it is important, I will explain you. But up to this, do you understand? Up to this, what I said,
Yeah.
everybody understood,
Yes.
right? Okay.
Yes, understood.
Yeah. So I will go to the practical aspect of this. Okay. Guys, you remember this one from the LS learning systems? Neural networks?
Yes.
Yeah.
Yes.
So we will use neural networks to identify the image, whether it's a car, human, or bicycle, or truck. So, in the modern cars, sometimes they have this traffic sign recognition cameras, and Tesla, they have, they can recognize Actually, it's a human, car, or motorbike, or vehicle, truck can recognize Teslas because they have these neural networks from that can identify. But how do these neural networks work? It works in a we call it as CNN, convolutional neural networks. So we do convolution, but in a neural way. So just high level. So this is a CNN actually. Yeah. So if it is a car image, this is exactly the same filter you applied. This is exactly the same filter. So whenever you see that kind of edges, one part is black, one part is white, it can identify the exact position. And when it can identify the position, like for example, can somebody annotate my screen and exactly show me a match for this part on the real image? You can just take the annotate and show me in the screen. Just you can write it in my screen. And can you show me a matching position from this image? No, it's the other way around because we should get the black in the left side, white in the right side. No, see, it is in here because in here also white is in the left side, black in the right side. So we need to get the black in the left, black in the left, black in the left is in here. See, black is in the left side, right in the white in the right side. You got it?
Yeah, but Gayan, won't this be also right? Like the black on the left side and white on the right side?
Oh yeah, you mean okay the
Yeah, this is what
yeah
I
yeah
yeah.
oh yeah. But yeah
It's
yeah.
a
I thought
similar
you
thing, right?
marked the wheel. Yeah, I thought you marked the wheel. No, yeah.
No, the wheel and that base together.
Yes,
So,
yes, that's true. That's true.
okay.
So now for a moment we will think about consider only the wheel. Okay. So with this filter, we can identify this part of the wheel. And computer knows, you saw the program, MATLAB program. So it can put a dot. That's mean computer knows where that exact point is. Likewise, so we can find another good filter, this one. And it can identify this part of the wheel. And something like this, it can identify this part of the wheel. Likewise, with all of these filters, you can identify the whole wheel. Okay. So it's happening on a one layer. When it comes to second layer, we will not get the raw image. We will get something like part of the wheel, like these kind of things we will get. Okay, it's already identified. Then we will apply different kind of filters. Maybe in the next filter, it's more like this kind of filters. Now in this filter, this part is black and this part is white, something like the bigger filters. This is the very basic filter. Then it can identify the whole wheel, then whole car. So then from your image, initially computer, when you feed the image into the computer doesn't know where the car is. But with this technique, you understood, right now we know how to write this program. So with these filters, we can identify exact point, then we can improve it in the next neuron layer. Likewise, then the finally can identify the car. So it knows where the car is. And when we add more layers, it can differentiate it's a car or human or lorry or truck or whatever. So this is the whole concept. You got this, everybody?
Yeah. This is kind of okay. Yeah, got it.
Yeah. This is the whole concept. Then the thing is, you guys remember he took the derivative of the image in the lab. So this original image we can filter little more. Like this is like to make it little easier and make the accuracy increase. Then we will do the rest of the things, like we will do some calculation on the Fourier, and if there is some noise we can filter it out, and we can identify the edges directly. Like let's say for example, without any of these things, we don't need the fancy colors of the car. If we can exactly get the edges of the car like this, our calculation will be very easy, right? So then we can match it very easily. So like I will explain you. Like when you take the derivative, first derivative of this car, you get only the edges. Something like I can send you some show you one dummy image. So when you take the first derivative of the car, you will get somewhat similar to this. This is not exactly, but we have similar image. I can explain you, but something like this. But when you get something like this, you like your filters will work better, right? Because your filters, it has only black and white small pieces. Yeah. So now we'll move forward. Okay. On the first lab, this part we understood, right?
Yeah.
Yeah.
Yeah, yeah.
Let's see. Take what's the second part. Okay. This is the same thing. We use the eye and find where the eye is. See, you can see the white dot. Exactly now, computer know where the eye is. So it is more important. It's like, you identify where the wheels of the car, then you can identify the way the car is. This is same like that. Yeah. So I can explain. I can take more time and explain similarity image also, but I believe last parts are more important. So we'll move fast.
Okay.
Yeah. Now the thing is, when we introduce a noise, we introduce a noise here. When you introduce a noise, it's a lot more difficult because these are very sensitive to noise. So that's why I can still get a match in here, but when I increase this count, you can see, I believe my noise should be, noise. When I increase to maybe 0.5, I will not get a match. See, I'm not getting a match in the same position.
Yeah.
Because I believe it's too much noise. I can little bit reduce it because in here you cannot find anything. Maybe 0.1. Yeah, exactly. On this you can see. See, you can see it appears a match in here.
No.
See,
Yeah.
not the eye position. When you increase the noise, like it appears here. Anybody remember in the lab when there is noise, we applied low pass filter to cancel out the noise.
Yes.
Yeah. So when you apply low pass filter to cancel out noise, like I can show you that lab itself.
It will kind of smoothen the image.
Kiran, you remember which lab is it? Like, is it lab 4 or lab 3?
I don't know.
Something like lab 3. Let's see. Yeah, I think this one.
That is this one.
We introduce noise also. Not this.
We multiply it with a Gaussian filter or something.
Exactly.
But I don't know.
Yeah. So what we can do is for those kind of scenarios, like we cannot if the original image has noise, so like we cannot match it. So it's very sensitive to noise. So what we can do is as a solution for the original one, we can just apply like low pass Gaussian filter, and it can reduce the noise. Or if this is like your real scenario, like if we are getting some noise, then what you can do is you can apply a low pass filter, so it will fix your problem.
Okay.
Yeah. So I will go to the second part. This is this calculation we did. Okay, this one. So in the Fourier basis, how to calculate from the not the Fourier, I didn't start Fourier yet. from the basis how to calculate the image. You remember this, guys? Like you have some bases, and you have like if, when you have the coefficients, how to calculate the image back. Let's say okay. This is just a concept, because in the Fourier, we will have Fourier coefficients. Then from that only we construct the image. But this is just a starting point. Yeah. So let's say you have 4-pixel image. To reconstruct this image, yeah, in here exactly. So to reconstruct this image, so this is your original image. You have 0.5 here, 1 here, 0.5 here. So this is your original image. Okay. So this is 0.5 inside, not that much dark. 1 inside, it's full white. 0 inside, it's half dark, because -1 is if the values are varying from -1 to +1. So -1 is the darkest spot, and white inside it is 1. So this is your original image. And let's say you have these 4 Fourier. I mean, if you have 4 pixel, you need to have 4 bases. And if you have 8 pixel, you need to have 8 bases. Yeah. So let's say these bases are stored in your computer, and I have bases in my computer also. What I can do is I can calculate the coefficient. I can directly send the coefficient to you, and you can recreate this image. I saw, yeah, these are the coefficients. See, so now I don't have I can take my notebook from here. It has image also. Let's say I'm not sending you the whole image. You store coefficient in your computer. I have the coefficient in my computer. So I'm just sending the, sorry, you have the bases in your computer. And my computer also, I have these bases. So when I send the coefficient, what happens is, first part of this, it's multiply with the first basis. Second part of this, multiply with the second basis. You can see the values. When you multiply with this, you get 2 by 4, 2 by 4, 2 by 4. And this one, minus 1 by 4, 1 by 4, minus 1 by 4, 1 by 4, like this. And the third value, you get multiplied with this basis, and this get multiplied with this. And when you add them together, you recreate your original image. So that's why they put this f hat, because it's a recreation. It's not the original one. We just recreated it. Okay. So this is how we recreate the images in Fourier also, using the same concept. But remember this concept. Now we'll go to the Fourier. Yeah, this is exactly the same one. Yeah. So I will directly jump into the Fourier. But before jumping, I will start the lab 2. Let's see, just a minute. I believe I close everything. Yeah, okay. Yeah, I will start the lab. The whole purpose of first lab is to, identify the positions, because that was the main important thing. Everybody understood this modular his concept?
No.
Okay. Yeah, I can explain you mod also. Because he complicated it, that's why. Okay. So let's say we have this original image. Yeah, I'm getting low. Yeah, okay. Okay, this is the original image. I will start from here itself. When you have this original image, and when you convert this into Fourier, you get some values. But in here, let's say you Okay, you have only real numbers in here, and you get complex numbers in here. In here, you have the values between the real images. We know values between 0 and 255. But in here, you get the complex numbers. Complex numbers, something like a plus ib, something like this. So I can show you these values also. This is figure 5, figure 3. Figure 3, we get the Fourier SC. Okay. Can anybody see? Yeah, this is the one. Okay, this is, we read the image, and our C in the sense that is the Fourier image. Original image is F. So in here, we can see the F in here. You can see all, I mean, this is the whole your 2 by like 2D matrix. This is 255 into 255 pixels. So it's like an Excel sheet, but all the pixel values. This is the first position, this is the second position, like a pixel value. All these values vary from 0 to 255. You can honestly see it, right? And when I take my Fourier, like now I'm converting, I'm just taking the Fourier, then all these values are stored in C, variable called C. When I see the C, you can see it's complex numbers. See, all of these are complex numbers. So you get this, okay, in here. This is the real part. And this is, you can see the small I. So this is the complex part. Okay. So complex number you can represent in three ways. One is A plus BI format. Second format is cos theta plus I sin theta. Third one is EI omega. Okay. So can anybody tell me the different similarities of these? Okay, it's exactly like this. This A part, this is, you can see the first part, this is the A plus B, I is separated. Is it clear? This is A, this is B, this is the I. Okay, A is equal to cos theta. This is B equal to sin theta. This is your I, you can see it directly. Can you see it? Is it clear?
Yeah, yes.
Okay.
Yes.
Okay. So can anybody remember this equation in mathematics? EI omega equal
EI omega plus something, right? By
exactly. So you know now, you know that like if the complex number can be represented in cosine, it can represent in this format also. So whenever you see this, it's a complex number in the images, in the Fourier domain. Like any of these, you can just take it by E value. But in here it's different because that's like, you know, scientific number format. If I just double click, you can see this number is so long, like e to the 10 in the sense it's like multiplied by 1000. That's that thing.
Do 10 power minus.
Yeah, exactly. So this is here is different, just some notation, but this is the whole thing. I'll just show you my small note also. Some problem with all my things comes in other screen. See, you can represent it like this. This R is nothing but the magnitude. So I will come back to that later. So it's the same thing. So whenever you compute the whole idea is your original image was in real numbers, but whenever we compute, you got these complex numbers. Why you got complex numbers? The thing is, the Fourier domain, we have the images with two values. One is phase, one is magnitude. Phase and magnitude. These are the important things in the Fourier domain. So we had a real image. When we converted to Fourier, we got phase and magnitude. So these are the things in the Fourier. In here, real image, you have only the pixel values. In here, you have two parts. It's separable because it's like we know one thing. The magnitude it comes in here, and the face value. This is the face value actually in here. In the magnitude in here, this is the magnitude actually R. Yeah. So let's move back. We close this, and when I open this, I can explain you more. When you take this Fourier, you cannot directly just display it because it has the imaginary numbers also. So imaginary numbers we can see. What we can do is, I believe, yeah. So in here we just take the absolute in the sense we are just taking the norm of that. So we are just converting everything into positive. Can somebody tell me what's the difference between absolute and L2 norm?
What is absolute and
L2 norm?
L2?
It's actually nothing but exactly this one. You can see in here, these are the norm. When we calculate the norm, we call absolute P is equal 1. That means I will tell you how P2 is calculated. P2, you already know, this is Euclidean. X square plus Y square root. Everybody knows this, right? This is like triangular inequality. So everybody knows it. So this is we understand. And like L3, no, let's say P4, this one I can explain you. This one what? Can somebody tell me? X into 4 plus Y into 4, not the square root. It's like, you need to put a small 4 in here. You are taking like 4 power 4. Yeah. So, so in the if I write in the same notation, but I don't know, maybe we cannot write it. So it's like, this is absolute. This absolute in the sense, it's when this notation is 1. This is L1 norm. Absolute in the sense L1 norm, L1. So it should be like X to the 1 and Y to the 1 and something like this. But the whole concept is you will not get the minus values. For example, in L2 norm, for Y, like when you submit some values like 2 and minus 2, in L2 norm, you get
Square.
Square plus
yeah,
square.
2 square plus minus 2 square. That is also
it will become positive. Yeah.
4 plus 4. We get 4 plus 4. So in the L1 norm also it's the same thing. But yeah, so that's why we take the absolute, because the imaginary numbers. Why we take the absolute of the imaginary number? You know what is I? I is equal to square root of minus 1. What happened when we multiply? Yeah. So I can write something in here actually. Some example, maybe small one. I had it. Just a minute, guys. Yeah. So we will take one vector. Won't take much time. Let's say we have one vector. It's square root of 3 plus I. So let's take the L2 norm of this. Okay, this is how we need to represent it normally. But usually if it's L2, we'll not write this part. So what we need to do is square root of 3. We take multiply. Sorry, we take the square of that, and I also square of that, and square root. So this becomes square root of 3, and plus what happened to this part? Minus 1. Yeah. So you need to take the like this become 3, right? Yeah, this become 3. Become 3, I believe. Because it's it becomes 3. Yeah. So this become minus 1. So we get 2. I'm right? Yeah.
Yes.
No, guys. I made a small mistake. I will explain you. Okay. See, the same one I will write it in cos theta format. Like in here, there is one thing, cos theta plus I sin theta. In here, this I is represented in here, but this sin theta, it's represented by some variable in here. What's the variable in here? That is 1. That is 1. So you can see the same thing in these data matrices also. When you see this I, in front of this I, you can see some number. That is that part. Okay, that is sign part. The I is in here. So while taking the norm, we will not take I, but the term next to I, we will take it, sin theta term. But in here, it is that, you know, the hidden piece, it's a 1. Actually in here, if I just expand it, it's 1 multiplied by I. Okay. So when I take the L2 norm, I just take this term, and this hidden value, I will take it. If I write it like, you know, I'll change the color of my pen to red. If I write it like V equal square root of 3 plus 2y, it is easier to understand, right? Yeah. So in here, what we need to do is, if I calculate the value in here, it will be square root of square plus 2 square. But in here, if I write it, square root of 3 square plus 1 square. Yeah. So this is become 3 plus 1. So the value is 4, square root of 4. Yeah. This is how we calculate the norm of a vector.
So the norm will not consider the imaginary part?
We considered, actually. We considered this whole term is the imaginary part.
Basically, you're saying that it's the coefficient of the imaginary part, right?
Yeah, exactly. Yeah. While calculating the norm, this is how we calculate.
Okay.
And also, yeah, this is how we calculate the magnitude. This is also the magnitude. Norm of a vector, we call it as magnitude.
So this number 2 is actually the magnitude, right?
Yeah, it's the magnitude. Yeah, because in the Fourier, we keep the magnitude and the phase. Then what is phase? Phase is actually the angle. Okay, so I will explain it more in the later, but right now I will tell you how to calculate this, like the mathematically the calculation is happening. There are two ways we can do. Some of you, if you guys need to do the math again, this is very important, because in the Fourier also we need to calculate the exam questions also in the mathematics. Like in this time also, for the third question, we had to calculate the magnitude and the phase. So this is how you calculate. This is how you get the magnitude. And the phase, there are two ways you can do. One way is just take the vector, divide by the norm. This is equal to phase. This is the one way. So like in here, if you calculate it, let's say it's V hat. So our magnitude is 2. So it's like 1 by 2, dividing it in 1 by 2. And inside our original vector was square root of 3 plus I. So then we can just multiply this inside 2, and we get here 1 by 2I. Yeah. Then this is equal to I theta cos theta plus I sin theta format. See, this is your cos term and this is your I term. Okay. So now if I just write it, your cos theta equal 2. And can you tell me what this value is on the other side also? I can just write your sin theta equal 1 by 2. What's the value for? Like, what's the cos inverse of this? Or what's the sin inverse of this? This is equal to, theta is equal to 30. That's been 5 by 6. You can just take the calculator and check the value for like cos 30. What's the value of cos 30? We can just go to Google and see, 3 by 2. square root of 3 by 2. This is how you calculate the magnitude. But the general, there's a very easy way. Another way, we can directly take tan theta. This is how this is another approach. Without dividing the vector by its norm in here. Yeah, without doing this step, we can directly take tan theta. Tan theta. What is tan theta? Tan theta is sin theta divided by
Cos
theta.
theta.
Yeah. So what was your from the original vector itself? What is your sin theta? See, I told you, like, this is the sine part and this is the cos part. The original.
One.
Okay. Yeah, I will. Yeah, I will try the this our original complex number again. Our original complex number was plus I. I insist there is a one small one also. First part is represented to cos, and second part is sine. Cos theta plus I sine theta. Okay. So sine part is 1 divided by
Root 3.
root 3. So just take the tan inverse. Tan inverse 1 by 3, you get the theta. It is also the same.
Okay.
By the way, the answer is 30. We can just tan 30. We can just Google it and see.
Yeah. Okay.
Because if you guys don't trust me, I need to show it, right? See, we get the same exact answer.
Okay.
Yeah. So yeah. So just remember all of these things I did this one to show you in the Fourier domain. We keep the phase and magnitude. I just showed this, what is phase and what is magnitude and how it is calculated.
Yeah,
okay.
that's really good. Okay.
Yeah, because then we have the whole idea, right? In that case. Okay. We go back to this image, not to this one. Sonu, is it clear to you?
Yes.
Okay. Sajishna, is it clear?
Yes, good.
Okay. Lisa, is it so far clear? And Asha?
Yes, it's clear for me.
Okay. So we take this image, and when we convert, now we took the absolute. You know what happened when you take absolute? We take the magnitude. There is no complex numbers anymore. We are converting the complex part into the real numbers. Okay. So I will take this again. So when you take the FFT2, that means you are just converting this image Fourier transform. This is nothing but just take the Fourier, and you get the complex number a plus bj, like this you will get. But when you take the norm of this, you actually taking the real values. Just take the magnitude. So what we are displaying here is magnitude, but when we display, we get totally black image. The reason is now in here to display in the computer monitor, we need to display the values between 0 and 255. But when you see the value ranges from here, there is a small pixel in here. It's in white color, and another pixel, like all other position values, it's like 72,000, like very big range. So all the values are varying from 0 to like 72,000 and very big numbers. And when you scale those two numbers, like when you try to scale these into this scale, I can show you. We'll just zoom in. I can zoom in. Yeah. Can you see as a small white pixel? If I just click on that, I can read the value here. You can see the value is, what's the value? Index value, like 7 million. It's like 7 million, right?
Yeah.
Yes. Yeah.
Value
It's a very big value. Yeah.
It's a very big value. And when you check the value in here, like 41,000. Okay, it's like 11,000. Okay, so I will check all the value, like 3,000 something. Yeah, so like you can see like 1,000, see 900 something. So most of your values, you can see it's like, it's less than 10,000. Most of the values. See, all the values like 2,000, 1,000, 3,000, less than 10,000, all the values, less than 5,000, honestly. But all the values near to here, in the last dot, like I can write it like this. All the values in this majority region, it's like less than 5,000, less than 5,000. But in here also like 50,000, right? But suddenly in this value, in the last corner, it became 7 million. So when you scale that into 0 and 255, what happened is all of this area, when you fit this, it becomes 0, right?
Yeah.
Compared to this value, 7 million. Because when you assign 7 million, 255, then this is a very small scale, right? So how you display 1,000? You will get 0. You got this thing? Anybody understood?
Yeah. This is yeah, I got it.
Once
But
threshold, it
can you just everybody just unmute and tell me, is it understood? Because just next part is based on this.
Gayan, can you please explain once more?
Sure. Okay. Because don't keep any doubts. If you have doubts, just ask, because this is not like the lecture, so we are just like one-to-one trying to share the knowledge. So if you have any doubt, ask me, because these are not the hard ones, but maybe how I explain is not clear. That's what. So we have a small scale. Our scale is starting from 0 and 255. 255 inside, this is white. Here it's black. And our original values, it's varying from something like 1,000 to 7 million. 7 million, I will just put zeros and see, like, then.
This is the complex number, right? After you converted this image?
Yeah, it's a complex number. Now, complex number also we convert, we put the norm of the complex number. So that is magnitude. It's actual real number now.
Okay.
So extract the number when index, it represents the number, the norm, like magnitude. This index is nothing but exactly the pixel value in the original value when you take it, like when you take the magnitude. Because now we are trying to this like this range, this started from 1,000 to 7 million into 0 and 255. But the thing is, majority of this here also like up to here, I can say up to here, all the values be less than 5,000. Maybe 5,000 is sitting on here. So in here like 50,000. Okay, so 7 million divided by 50,000. So you get 150, 140. So this point is 140 times brighter than this point. Okay, this is 50,000. Yeah, I need another 0. So this point is 140 times higher than, brighter than this point. So if you assign this point as 255 white, and if you assign this as black, and all of the values, all your values, it's sitting in here actually. All these values, yeah, all this scale, because you are just scaling it down. So that's why you get this black image. Understood?
Yeah.
Asha, is it clear now?
Yeah, it's clear now. It's clear.
Okay. Yeah. So we cannot see anything. So we need to have come up with a solution. What we can do is we can take the log. What log does is, we can draw you something. Have you guys remember during the COVID time, when the COVID graphs, there was one website called, I cannot remember the name exactly, but to see the pattern, we can, I mean, sometimes COVID comes and we cannot find the patterns. So they convert the graphs into log graphs. Anybody remember?
not
Yeah, there was some website, right?
Yeah. So
I remember,
yeah, we can take it, like you can take the COVID world meter, right? Yeah, I think So exactly, okay. So in here you cannot see any patterns. Let's take a specific country, maybe. Okay. Then what the thing you can do is you can, if you go to this log, you can see a pattern. See now, like the date, is it saturated or not? You don't know. But when you convert this graph into log, you can say, okay, like 2020, it came high. Okay, now it is like saturated. Now there is no issue. This is very clear, right? By looking at this, you know this is saturated. But like, by looking at this, can you get any idea? Can you tell it is saturated?
No.
No. In here also we can do. See, now the total COVID cases, you can see it's like saturated, it's stable now. But looking at this graph directly, but looking at this, can you tell anything? We cannot predict it,
No.
right? Yeah.
No.
Yeah,
So-
yeah. Correct.
Yeah. So the OLS log, what it does is, it's like the whole scenario, it's scaling down. For example, if you have a graph like this, log will convert it into a linear graph like this. And if you have a linear graph like this, log will convert into a stable. Okay. So it's so that's the log will do, like it's scaling down. So in here also what we did, we applied log into this one, so it can scale down. Then we can start seeing the things, just like what happened in COVID graph. See, it's nothing but we just apply the log into the same one. Now we can see the things, because now like the earlier, if the difference is like 100, now it's displaying as 10. If the scale was previously it was 10, now it's scaling like 1. You can see the thing like 10 displaying as 1 and 100 scaling as 10. So earlier difference between it was 90, but the whole scale, it's like shrink, right? The major expand part, it's shrink a lot. Like if the down line is like this, so this whole thing, like when I fit into this scale, it's what happening in sense. I can tell this distance also represent by in here, and this distance also represent by here. It's like a similar scale. Yeah, scaling down. So when we apply the log, I can show you. Now we go to the code. To see here, then okay, we apply log. Okay, now when we apply the log, we got some image like this. But the thing is, now the modular parts, like have been said, it's not clear. Now this is the mod forms. So the thing is, in normal graph mathematics, we know this is our y-axis, and we know this is our x-axis, and our 0, 0 is here. The plus numbers, it goes in this direction, and minus numbers goes in this direction, right? Is it clear?
Yeah.
Okay. And here y-axis also, all the plus goes upward and all the minus goes downward. Just a minute, guys. Okay. Yeah. Then in here, the thing is, in here is the 0, 0. All the plus, it goes on this side, and all minuses, it comes from other direction. Okay. Because of the mode.
Okay.
Sorry, because of the
This is because of the mode
Mode.
operation.
Mode
Because of the mode
operation.
operation, for example, if you give the value 10 here, if you represent 10 in here, let's say your 10 is in here, and what is minus 10? It is from here, starting from here, walk backward 10. This is your 10. This is your minus 10.
okay. Fine.
Yeah. This is how the mode works. Like the thing is, okay, let's say whole duration is like in a here to here distance is 255. Let's say 256.
Yeah.
And 256 plus 128, what's the value? You get some value. Okay, we don't need to calculate it. And when I mod this one, submit this one, what happens is it goes 128 in this direction, and starting, because again round rotation, that's why he said it's going round and round. 128 goes here.
Okay.
This is, you are sitting in here.
Okay.
So what we can do is, if you want, I can take that exam paper also. I can explain that. And there's one question. Sipshak, are you there?
Yes, I'm here.
Okay. Can you take that exam paper and tell me that, there was one question related to mod. Can you tell me exactly which page?
Yeah, I'll just check.
Okay.
1 second.
You have a question paper?
Question paper is not like I already shared with that guys. Previous some
Model question paper.
Okay.
She already shared in our group.
Okay.
So in here, what happens is, so what we did, because in normally the 0, 0 should come into the middle, but the mod, is it understood, or should I explain more?
Yeah, I understood.
Yeah.
God is good.
Okay, I can show you one small program where, if you have small doubts, then we can clear it. So I will just run this. So, okay, let's take this one. I will delete everything up to here. See, you can see this one, especially more specifically this one, -10. That's meant down from second. So what it should do is, it should work backward. I said it should work backward. Like if your scale is like, 0 to 256, like -10, it should work backward 10 times. Here, this is -10. Like you need to work -10 backwards. So your value should be 256 minus 10. That's mean 246. See, we get the answer. Yeah. So in here also, like if you work 266 and 266, that means you are working again into here. You are coming back in here. So you should get 0, your starting position. In here, like let's say your starting positions. What is your starting position? It is 0. And when you walk the same distance, you should start. You should get your start position again. Understood, right? And tell me what's the value if I make it 267? What's the value?
-1?
No, it's 1.
1. Okay.
Yeah.
It's mode. Oh.
Yeah. No, it's like this. Like this is your scale. This starting position is 0, and this is 256. When you go on this direction, and you are appearing in here, you are coming to the same position.
Yeah. Okay.
So when you
then
go one more,
256.
yeah.
Okay. It's 1.
Yeah. In the minus also, remember the minus mainly. When you work backward, it's starting from here and going back from the corner. Understood, right?
Yes, understood.
Okay. So we'll go back to this one. Okay. Now what we need to do is, normally in like on the school time and everywhere we use the things like this. We took the middle position as 0, 0. So we need to align this. We need to take this 0, 0 into the middle. So in this image, what happens is, all the positive number, it came on this side, all the negative numbers, starting from here, it came this side. So that's mean, if I just move this position into here, all the plus numbers will be in this side. And all the negative numbers, that's mean this part, I need to cut that part and take it into here. So this part of the image, I need to move down. If I move it down, just a minute. If I move it down, what happens is, now all your increasing numbers goes in this direction. All your in this direction, downward increasing also goes on down. And your upward numbers in here comes from this direction, right? So that's mean this circle, where it should go. Number 1, number 2, number 3, number 4. Tell me the position for this.
That 3 should go to 2. Does it have to go to 2?
Yeah. This one will go to here. This number 3 will come here. Number 4. Number 4 will come here. Is it understood?
Yeah, again, can you tell me like what are you trying to do here?
Yeah. So I'm trying to, right now the 0, 0 is here. I need to take the 0, 0 into the middle. So when I take the 0, 0 into the middle, so if I just divide this image into 4 parts.
Okay.
Yeah. So I know my increasing numbers from here, because in the normally what happens is in normal mathematics we had the 0, 0 in the middle. We had a 0, 0 in the middle. Increasing numbers, it goes on this direction.
Now it's because it's in that corner, and you're bringing it to the middle, right?
Exactly.
Okay.
Yeah.
So the quadrants will interchange. Yeah.
So when you interchange it, like, is it understood for everybody?
Yes.
Okay. Sajishna, what about you?
Hello. Can I
Uh,
found that question which you
you
asked?
found you found
Yes.
it or not?
Yes, I got it.
Okay. Can you
I'll
send me?
just make sure that is the same. I'll
Okay.
just share the screen.
Okay. I will. Okay. You can share. I will stop sharing.
Is this the one?
Yeah, this one. So, guys, let's try to calculate this one also. This is the mode 1.
Yeah.
So in here, our scale is what? What is our scale? Okay, we have an image like 255 rows and 512 columns. So this is whole length is 512. Whole length is 512. This is whole length is 255. 256 or 56. Okay. So now there's a vector.
Yeah.
64 by 128. So 128 is in this is 255. 128 is in here. 64 in the sense here. So this is your first position. This one. This is in here. And the second one is 128 by
64.
64. 128 by 64. So somewhere in here. Second one. So I will use a different color for that. 64. Okay. Then he's asking the position value of this. Okay. Now I'll use my blue pen here. Okay. So it is like this is the row. So we'll go on row direction first. We need to go. Okay, I'll start from here. We need to go 256 times. That means I need to go half distance. Then I need to go 64 and 64. That means 64 and 64. So I'm in directly in here. Okay. Because in the middle, the value is 256. And this is another length of 128, right? This is 128 length, and this is also 128 length. If I go it.
Yeah.
128 like this. So one part will be in here. No, this is, I believe, the other way, right? This is row.
Yeah. The row is right.
Yeah. It's a row. So I will mark it in row. Okay. Goes to 56 times down. I will start from the other angle. Yeah. So I will start like this. Go to 56 times down and 64 and 64. Oh, 120. 256 times down. Then upper start from, because it's round operation, right? Go 64 and 64. So it will be somewhere in this axis. Yeah. Then in the column, I need to I have minus 512. Minus 512 in sense starting from here, I will go here this direction. Again, I'm sitting in here. and plus 128, plus 120 in the sense I'm going 128 this direction, here to here, 128, and minus 64, again going backward. So exactly in here. So I'm landing on top of here.
Yeah.
So I exactly get this value that is equal to this one. So the correct answer should be this. This is 9. Yeah. Got it, right? This is how you find it.
Yes.
Yeah. So still we didn't explain the like Hermitian symmetry. So then if you get some values in here, then I will explain what is Hermitian symmetry. Sipsia, you can stop sharing.
Gayan, how did you get the correct answer is 30 plus 59? You sum it up and you subtract everything. Is that how?
No, we didn't do any. Like, which answer? You mean this one? No, it's
Individually
it
we can do, maybe, or
no,
else we can sum up and we can do. Both way we'll get the answer.
we pinpoint to the exact point. See, previously,
yes, I got this point. Yeah, I understood this point that you said that you found the point.
Yeah,
but
its value is
how
already
do you...
given. See, value is already given. See here.
Oh, okay.
It's the same value because this was the previous point. Previously, there are 2 points given and their values also given. So we landed on top of the same point.
Okay.
Understood?
So why is it not 15 plus 30i?
15
Why
plus
is it not 15 plus 30i?
15 plus 30. No, this see, I mean, when we check the values, we landed on this point. But the value of this point, it's already given. This is the value, 30 plus
Okay.
59.
Oh, we had already that. Okay.
Yeah.
Okay. Fine.
So we gave the points, and in the modular operation, when we went round and round, we landed on top of the same point. So the value is already given.
Yeah. Got it.
So there's something called Hermitian symmetry. Hermitian symmetry in the sense. Now the next part comes. So whatever the values in here, it will appear in here. But the thing is, it's complex conjugate. So if that is the case, but in this case, it is not the case. So I will explain it now.
Okay.
Picture, you can stop sharing. Okay. So now the thing is, now I will go a little fast. This image is clear, right? The last image. So when we align everything, like when we move the 0 position into here and the 0 position into here, what happens is, this is part 1, this is part 2, this is part 3, and this is part 4. Asha, your camera is on. Then what happens is, number 1 comes here, number 2 comes here, number 3 comes here, number 4 comes here. Is it understood how this happens?
Yeah.
I need to hear from everybody.
Yes.
Okay. Then this is now the concept is something called Hermitian symmetry. You can see this pattern, this pattern. It's repeated in here. It's exactly the same thing. Can you see?
Yeah.
And this,
yes.
It's in here. Okay. And this line, it's in the other side. So it's symmetrical, but the thing is, it's upside down also. Like it's symmetrical on all axes. So if it is x-axis, it change the direction x-axis, inverted to x, and y also. If you have y, it's inverted on y also. On all axes. Right now we have only 2D, but if we have 3D, 4D, 5D, if you have multiple dimensions, what it need to do is all axes it need to invert on all axes. Okay.
Yeah.
This is happening here. And the thing is, when we check the values, actually we are checking the magnitude only. We don't check the complex number. So we'll do one thing. We'll pick one number in here and we'll compare it in here. Okay. So because these matrices in MATLAB, it's exactly in one Fourier. It's like C. Okay. So the value in here should represent in the other side, down, last corner. You got it? So now we are trying to look a value in value in here. Because of the Hermitian symmetry, it should be in here.
Okay.
So now we'll try to verify it. This is the second row, second column, and from down. Okay, somebody need to take the value of that. I'll just copy the whole. No, I'll just take a screenshot. I think it's better. Step into. So this is the one we have it in the. I will took it. Let's see. Okay, it's visible. So I'll go down to the last corner. Oh, sorry, not this image actually, because we need to
Yeah.
the
No.
SFF like we need to take this image. Now I compare this image. We need to compare this one.
Yeah.
We shift it 10 only.
Otherwise, the quadrant will be different.
Yeah, exactly. So we'll take that image. I believe it is in C. Then we reconstruct. No, not reconstruct. We need this one F50 shift. Can you see anything F50 shift in here? Otherwise, we have reconstruct. We have C here. No, we don't have. So we'll do one thing. We'll take C and directly we'll do F50 shift. Yeah, okay. Now I should get a new variable called byam2. Okay, we have this value 27. Two, 7, 3, 9. Okay, we have the value in here. Why we are not getting the value in here? Because the thing is, I can explain you the reason. If we have some odd numbers, number 5 pixel by 5 pixel thing, okay, we have 5 columns like this. If I take it symmetrical, it can rotate this across this axis, okay. But if I have 4 pixels, what happens? Like even number, what happens? So it need to have axis, so it will try to rotate across this axis.
Okay.
So that's why you don't get it exactly, because the original image has like 256 numbers. Like it's not a like even number. If you have an odd number, then there is no issue. So what we will do, we'll take some pixel inside. So like we'll take 3 by 3, this one, exactly this one. Then in the other one, we should get it like, you know, that's 2 by 2. 2 by 2 position, second column, second row. So this one we'll take a screenshot now. But if my grid is like having odd numbers, there is no issue. So my number was 7, 5. So I believe this one. Oops. Okay. Like here, I should get the same one. Let's see. Yeah, this is the same one, right? But one difference is, can you notice the difference?
Yeah, 1, 5.
It's like the same thing, but there's one difference. The complex part, I'll give you a little hint. Complex part, check the complex part. Here it's minus, here it became plus. Notice? Okay, what is complex conjugate? Complex conjugate. If you have a plus,
I see.
yeah, bi. So complex conjugate of this
A minus B.
exactly
minus.
a minus bi. So if the numbers in this axis, if your number in the complex plane, usually real plane in this side and complex on the other side, right? If your number is in here, it gets a symmetrical one in the other side. But this is if it is plus a, it is minus a. So we got the same thing. In here, it is symmetrical, but the thing is complex part, it got the conjugate upside down. Okay. Yeah. So that's the thing. Okay. Now tell me, if I have half of this Fourier, can I recreate the one? And how should I do it? If I have half of this.
Yeah, we can reproduce. We can copy
Yeah.
it.
Okay. What's the method? Now we saw two
You know,
things.
which half one, Gayan? Sorry, I
It
don't
doesn't
get
matter.
which
It
half
doesn't
you're
matter.
talking about.
Any half, because you can see in here, this is exactly equal to here, but upside down and complex conjugate. So we can see a pattern here. So if I don't have this first half, if I don't have the first half, and if I have only the second half, can I recreate the image?
Yes.
Yeah. What you
Yeah, you should be right. Yeah.
yeah. What you should do? You should take we should copy a half to the other side and make it upside down. Upside down and left and right, like all axes, you need to change the direction. Then complex conjugate. Okay. Then without any data loss, you should get the image.
Yeah.
So this image you can store in this way. So if the original image is 5 MB, now you can save like 2.5 MB, you can save it, right? It's like half, you can directly cut it down without quality loss.
Okay, you're just trying to compress this.
Yeah, directly we can do it, right? Without any
without the full image.
Yeah, without any quality loss. So I believe the second part I did somewhere. Yeah, exactly. This is figure 4. Let's see figure 4. Figure 4. Okay. 0 to 128. Okay, in here. Okay, rows. First half. This is the first half is selected, and first half on the columns and all rows. I'm setting it to 0. So the values are now destroyed. In C1, when you plot it, you can see one half is already gone. Then second what you did in here, just taking the conjugate of the values. Anyhow, whatever the selection, we need to get the conjugate, right? We saw it now. So in the minus selection, why you select minus? Now you are not selecting from 0 to 255. You are selecting from 255 into minus. Sorry, to 0. Because
from backwards, right?
Backwards, because we saw it's like it's two parts like this. If a man is sitting in here, now man is sitting in other side, and also left hand is in the right hand. It's like this. So this is why in you need to make it upside down. And columns, it doesn't matter actually. If you just think it, then you will understand. I will just show you the image. If you make a copy of the other side and make left and right shift, that is fine, right? The up and down, if you shift it,
column will be same.
Yeah. If you just make a copy and upside down, change it. No, other side also we need to change it. Let's see what he has done. Okay, cool. 0 to 128. Rows he shifted upside down, and the columns.
While destroying, he has given minus. Column. T1.
Oh, okay. Yes. Yeah.
Yeah.
So then you apply the conjugate. Then you apply the conjugate. So you get all the values back, and conjugate also we are getting it. But just tell me, is there any data loss or not?
There will not be.
There won't be any data loss,
Yeah,
right?
there should not be.
Yeah. There shouldn't be any data loss. But if we have, I mean, when you calculate it, if you get a minor data loss, that is only because that I told you, like, if your matrix originally it's like odd and even numbers, we saw it. Yeah. So that's the only possibility. You will, if you get a difference, because in the one pixel, like in the even one, you cannot uh, take it fully symmetrical. Yeah. So that's the only difference. Otherwise, you can get it perfectly. So this is the Hermitian symmetry. If you see the word Hermitian symmetry, this is what. Okay. Guys, shall we just take like 10 minutes break and we'll come back?
Yeah.
Sure. No
So,
problem.
Yeah, sure.
I'll put a timer here. Timer for
Okay.
10 minutes. 10 minutes. Okay. You can see the time. Time. Yeah, I will start the timer now. When the time is over, everybody come and join.
Yeah, sure.
Okay.
Yeah, okay.
Good. All good.
Hello. Is everybody back?
Yes, yes, I'm here.
Okay.
Yeah.
So I will take the Fourier bases. Second part is now we need to explain the Fourier bases. So it's like this. Okay. So this is how you construct the Fourier image. So let's say you have original image. Every pixel you will multiply with the Fourier basis. No, the original image you will multiply with the Fourier basis, and you will present it in every pixel in the Fourier basis. Fourier coefficient. Okay, I will explain again. So original image, let's say the size of the original image, it is 256 into 256. So you will multiply it with the first Fourier basis 1, that is also size 256 into 256. Then resulting value is the Fourier coefficient 1. So you will save it in here, first pixel. And the second one, take the original image, multiply with the Fourier basis 2. Fourier basis 2 is nothing but it's also same size. You are just multiplying with the same size one. Then you are saving it in the second pixel like that. So the Fourier image, actually it contains every pixel, it contains the Fourier coefficients. So yeah, this is this is another representation. Like the original image, you are just multiplying with the Fourier basis 1, and you're putting the value in here. This is understood, right? Yeah.
Yes, yes.
Yeah. But there is one constant term also in the book. It says 2 pi by t. So that is also will multiply, but that's not the important thing. Yeah. So the thing is, these Fourier bases, the Fourier basis first has a low frequency and 2 has a higher frequency, like that. So the frequency of Fourier basis 1, it is the lowest, and the 2 is double. Likewise, the frequency will increase from here to here, Fourier basis, and from downward also it's increasing, because now in this in this one, my 0 and 0, it's in here. So we can check it. Yeah, this one I believe. Okay. In here, E1, it's from the Fourier base. You can see the base. These are the Fourier bases. So I'm making one Fourier basis image. So it's 256 into 256. So the first position, first row, first column, this one, if I just take that value out, and if I just print it, so that's the one you are getting in here. Okay. So when you increase on the column axis, so this is the row axis and this is the column axis, 1, 2, 3. You can see my 1, 2, 3. It's yeah. So 1, 2, 3. You can see it's increasing, but it's increasing on the column axis, not on the row axis. So row axis you have one white space and one is white space, and here also it is same in row, and only the column. Column I had one here, and here it's 3, and here it's 4. So it's increasing frequency on this direction, and this is why I'm telling this is frequency. This is, you can see exactly like a cos wave. Cos 0, you get the highest. like this. And in here you get the lowest, and here you got the white, and here you got a black lowest, and here you got a height again. See, this is exactly like a cos wave. So it is frequency. This is the phase. This is the phase. I told that Fourier has two things: phase and magnitude. Yeah.
Yeah.
And
Yeah.
yeah. Okay. So when you go downwards also, see, I mean, this is only one axis I increase. So I will just ask one question. If I change this to 10 by 1, what happens? Previously, can somebody draw lines in the screen? Previously, I got lines like this. I will show the image also. Previous image. Yeah, this is the 1 by 10. What happens if I make it 10 by 1? I get 10 lines in here and only minor changes in the up, because I'm increasing the frequency on the row axis now. Okay, so if I just run it, see.
Yeah.
Yeah. So you understood this one, right?
Yes.
Fourier basis.
Yes, yes.
Yeah. So
Yeah.
and now, like if I take the image like this, original one, in this axis if I go, and in this axis if I go, the frequency is increasing. And what if I move the 0, 0 position into the middle again?
And the quadrants will change.
When you go in this direction, frequency is increasing. And when you go in this direction, frequency is increasing. Up also increasing. When you move away from 0, frequency is increasing, right?
Yeah.
So that is why in the middle part, it has low frequencies, and outer, that is why you get high frequencies. That is why when we put these round shapes, so we call it as low pass filters, because when we select in the middle, so that is a low frequency. When you put a Gaussian, when you put Gaussian or circle or whatever, Gaussian also like a circle, right? I will come back to that later, but it's like a circle, and then what? That is why we call it as a low pass filter, because you are selecting only the middle. Middle has low frequencies. I just showed you. Understood?
Yes.
Everybody understood, or you need more clarification?
Yeah.
No,
Kind of understood.
I
Yeah.
understood.
Okay.
Yes, yes.
Great. Yeah. So I will show some extra thing. And this is the image. I mean, this is the Fourier. If you just pass only the low frequencies, you can reconstruct this. Only the low, without anything. So you will get some kind of small pattern, but you can see overall, like that is more important, right? Like almost you can even you can see it's only very few values, right? With comparing the original one. So, but it's constructed this perfectly. So the low frequencies are more important than high frequencies. And if you just pass the high frequencies, you will get something like this. Now we cut down the low frequencies. It's like 1 by 10, right?
Yeah.
But when you have all high frequencies without low frequencies, you cannot get it back. So, but you get all the borders. Borders are very sharp. But if you go back, I mean, borders are very sharp. All the edges you will get in high frequencies. But when you get this, but you can see all the edges are blurred. Okay, so that is why. And here it says Gaussian smoothing, but it's nothing but when Joseph said we add the interpolation with the Gaussian. So like we in the class we never constructed images like only with low frequencies. We actually construct the image by applying the low frequency filter, then we interpolate with the Gaussian. But we can create it like this one also. But when you make it with the Gaussian, you can see it's make the edges smoother. Yeah, and in here it says the face is more important. See, in this image, we just destroy the face. We destroy the magnitude, but still with the face, you can recreate the image. You will get something like this. But if you just destroy the magnitude, you will not get anything. Yeah, this is some other thing that this is some just to remember the mobile phones. We have this accelerometer. So when you move the mobile phone every direction, it can capture what's acceleration on each axis. And like you may notice when you take the photo from your mobile phone, sometime from a good mobile phone, it's better than a DSLR. The reason is in DSLR cameras, it doesn't have this accelerometer and those things. So camera need to be very still. But in the mobile phones, so it has accelerometer. When you take a photo, it can at the same time it can capture what's happening on the background. I mean, my mobile phone is moving or what's going on. Then in the Fourier domain, when you convert this into Fourier image, and this is your acceleration separately captured one, you can directly in the original image it has a data plus the movement. The original one you have the data plus the movement, and the blur one. This is actually like perfect data plus movement. But you can directly reduce movement in the Fourier domain, then you can get the original image. I mean, without a blur. So mobile phone will take the image, blur image, and it can capture this one from the accelerometers. Then it can directly reduce it in the Fourier. Then you can recreate a perfect image. So like some use cases of Fourier, it's a good one, right?
Yeah, it's a good one.
Yes.
But the thing is, these are very highly sensitive to like noise. So in this one also, like it's a big problem with noise. So we'll go to the next one. Before moving to the next one, I will just see if I can. Okay. There is one chart in our book. Yeah, this is the same thing that FFT function. This is understood, right? That like one more thing. If you take a Fourier, Fourier and Fourier inverse, you understood the difference? If you take a Fourier transform of an image, now this is the original function, and when you take the Fourier, you get the capital F. And if you take the Fourier again, Fourier transfer again, without no Fourier inverse this time, directly. Let's say if it is Fourier inverse, you should get the original function back again. But in here, if you take the Fourier, you get the image, but it is inverted. In all axes, it is inverted. If you take the Fourier 2 times. So, okay, now tell me what happens if you take Fourier again, Fourier transfer. So we get a Fourier. We get Fourier. Yeah, we get Fourier, and I need to write like this way. So I have a function. I take the Fourier transfer, FT, then I get a capital F, Fourier of that. If I take the Fourier transfer again, I get a simple F, but it's inverted, like this image.
Yeah.
But if I take the Fourier transfer again, I will get a Fourier. It's maybe inverted one, but it doesn't matter. But if I take the Fourier transfer again, what you will get?
We'll get F now,
yeah. So if you apply the Fourier transfer 4 times, you will get the original image back. It's in the lab, I believe it's
in the lab.
Yeah, 7 point, I believe 6 or 7. There's one formula. Yeah, this formula sheet. This is very important. Okay. We have convolution here. No. Okay. This same sheet I just expanded and I just added in my book. Okay. So in this formula sheet, this is like the because there are a lot of math in 5, 6, and 7. So, but we can summarize into the important ones, because the proving these things is not important, but how it works, that is important. If you take a Fourier transform, I mean, this is the simple F domain. It's called is spatial. Then capital F domain, it's called frequency. I mean, familiar with these terms because that is how he speak. Otherwise, we will get lost in the lectures. So, in here, if you just multiply with a scalar, in the other domain, it's a division. But it's the function is divided in two places. One is 1 by alpha in the first, then omega divided by alpha. So the 1 by alpha part, it's actually shrinking the height of this. You can see the above 1, if the scale was 2, now it is 1, like that. So let's say in this domain, if you make a function bigger function, so this domain it's becoming smaller. So this is the main thing. In this domain, if you make it like this side, it's shrink. This domain it becomes bigger, like this. So all the changes it's inverted. Is it understood? Is it clear? Or should I explain more?
No, that is okay.
No, it's clear.
Clear, right? Okay. And this one is, if you do some change on the Fourier domain, it doesn't matter in the other domain. There is no effect on that. Do the same. Okay. So if you like this is if you do some change, for example, this change could be you are just shifting the image on one direction, or you are just rotating the image. And the Fourier, it's the same. So there's a lab for that. We just open the lab and see. I think it's in lab 3, right?
Lab 3. FT.
FT, yes.
Yeah, this one.
Okay. In here, so we have this image and we took the Fourier. You can see this, and you can see this image is shifted in this direction by 30 pixels actually. When you shift it, this is exactly the same. There is no difference in the Fourier domain. Yeah. So in the other terms, we can shift in this direction, or we can shift it down also. That's mean we can rotate the image also, right? So like when you take a photo from the camera, even if the camera is a little bit rotated, so it doesn't matter, it can still identify. So let's say, for example, in your vehicle, you have a traffic detection, I mean, the traffic sign detection camera. In the car computer, all the traffic signs stored in the one direction, right? But even if your car angle is a little bit tilted, it doesn't matter, it can still identify in the Fourier domain. You don't need to do any conversion. In the Fourier domain, it's the same, like the practical approach. Understood?
Yeah.
Okay. So we'll go to the next one. This is the taking the derivation in the take the derivation in the other domain, the Fourier domain. It just multiplication with I omega. This is important characteristic function. Characteristic function, when you take the actually inverse Fourier, not the positive Fourier, it's inverse. Yeah, you have the characteristic function in the Fourier domain. When you take it inverse, you get the interpolation function. So this is nothing but sin C. Everybody know what is sin C, right? Sin C in sense sin theta divided by theta. We call it as sin C theta. So it's like the we need to take the inverse of this. In the Fourier domain, we construct this and we take the inverse, so we get the interpolation function. We can use many functions for interpolation. That's what. Yeah. Okay. This one also understood, right? In here, the Gaussian, when you take the Fourier of Gaussian, only difference is this is just the constant term, because with this one we are just in the height of this and make the whole area to 1 for us to use it in the probability calculation, because in the probabilities total probability has to be 1, so just a 1 factor to adjust it. But in here, when you take the Fourier of this, in this one it becomes 1 by rho. So this is the important thing. And this is the linearity properties actually. Like if in this domain, if you can multiply, in the other side also you can. This is the scalar. There is nothing. Only the function get the Fourier transform, and the inverse of Fourier transform. It's there, but when it comes to conjugate, there is a
It
little.
will be 1 by a into f of omega.
This one linear.
Yeah.
Linear. What happens is if you take the there is no change on the constant terms, but only the function get we take the Fourier of only the function. There is no difference.
I thought that in the first property we told like 1 by alpha and alpha. Yeah. I thought 1 by a and 1 by b will come here. Yeah.
No, this is inside the function. This is inside the function, not here.
Oh no, on the first property.
In the top.
The alpha one.
Oh yeah, it is inside. This is inside. The thing is, this is inside.
Oh, okay. Inside the function.
Yeah, the a is here.
Okay.
Yeah.
Okay. Got it.
Yeah. So like, don't get confused with that. See, a is in outside. Yeah, what you're saying is true. If you multiply with alpha inside a or alpha, it's then 1 by, and here also we get a 1 by term. Yeah. And this is time reversal. Time reversal in the sense, if you just change the direction in this side, other side also we can do it. There is no issue. But if it is a complex number, if it is a conjugate, we get a minus term here.
Oh, okay.
Yeah, that's a one of a difference. But I will go 2 pages back now. And this is one more rule. I forgot to add it. Convolution. But before comes to that, I will explain what is convolution. This is, we can define it as convolution, but not t plus tau. This is convolution, but f t plus tau, it is not convolution. The reason is after convolution, there should disappear after integration. Okay. So when you integrate this, the tau should disappear. How we take the integration by tau? We take the integration by tau. In here, remember this whole function, guys. Like this one, you remember, right? It's also in the slide. I believe it's keep repeating. By the way, this is in slide number 6 or something.
615.
615. What's the page number? Tau time came like it's 506. 615, right? I think it's before that, maybe in 5.
815 or 615, it's repeated.
I think we got tau terms in here. They have actually set up equations with tau. Now I cannot find the place exactly, but I took it directly from the book. I think it's 7 actually, because in my book my note itself I wrote it like 7 here. Yeah, section 7. f of dt, I believe it's closer now. Yeah, I will skip it because it's taking time if I try to find it in here. Yeah, it's this one. You can see it's this one. Okay. So this is our original function, and this is our filter. Always G represent the filter, and this represent the original function. So in convolution, what we are doing, you can see what we discussed was we had the original image, and we have our filter, and we are moving the filter. Okay, this is what we discussed, right? For every pixel, we are just moving the filter. But actually, you remember Joseph said moving the filter is same as moving the original image. You guys remember that?
Yeah.
Yeah, because actually what he's doing in here in the map, he's moving the image. We are moving the image tau times. So this is, we are taking the integration by tau. So we are moving the tau from minus infinity to plus infinity. That means all the possible positions, we are moving the original image. We are keeping the filter as it is. Understood, right?
Yeah. So,
Yeah. And like by seeing this, you may realize, okay, then what if I just put the plus tau? Like minus instant going other direction, right? If I just apply plus tau also, there's no issue, right? But the thing is, in the convolution, but when we take the integration, this tau term should cancel out. Otherwise, like it's very like we'll get some like we don't want to get the unknown things into our equation, right? But in here, when you take the equation, integration, from the first part, you get minus tau. In the second part, you get plus tau. So it will get cancelled out. But if you use a plus term, you get a plus tau on the first part and plus tau in the second part, you get 2 tau. So that is why we will not use this plus tau. I believe we got some exam questions also, maybe like that.
Yeah, we had one example of this convolution.
Exactly. And this is with the, if you have two variables, x and y. So your g, like it's just, tau, this is actually tau by x, and this is your tau for y. And on x and y direction, both you are moving this original function. This is for two variables, like 2D. Okay. Yeah. So, and if your original function is like this, the tau, you are shifting it 2 times. In our case, 1 pixel. Okay. And put both function on top of each other, then take the top product. Okay. You just like, this is your move to a different place, and this is your original function g, f function, and this is, let's say, f function. Then second one is g, and you just take the like scalar product or dot product. So that is what the convolution is. So that means the higher position, it will be increased, and the lower position, it will be lower in the graphical way. But we don't need that much. But one more thing, take one function, then nothing else.
Again, what happens when you convolute this? When both these signals, when you convolute,
Come
what is
again?
the end product you're saying? Now, what is the convolution? Like, what happens when you convolute, take the dot product of both of this signal?
You will get for images, if you have a image, you will get like another image. Like if you have an image by like 250 to like say like 100 by 100 image, when you can convert this by 10 by 10 filter, you get an image size is 109 by 109.
m cross n minus 1.
Yeah, I will explain why you get that. But basically, when you multiply that, you will get another image. Same like your big one. Yeah.
What is the whole point? Like, why are we doing this convolution? Like, what is the The
We'll
whole
be
idea behind
shifting
it.
the original image, and we'll be multiplying it with the filter.
Convolution, it's like, you remember the first lab, we had the small filter, and we had this small filter like this, and we applied the image.
Hmm.
So likewise,
Yes.
yeah, if you have a, like, small filter, you can like, for example, you need to blur the image. Okay, like you have seen in, like, sometime, if you can add some filter to blur the image. So,
Yes.
yeah, that kind of thing you can apply. But main thing is you can cut down the computations. That's the main thing, because I had one video also, but I don't think I have it now. So, like, do you guys know Star Trek? No, right?
Sorry, what?
Star Trek, that movie series. So, like, it's like this. Yeah. So you have one spaceship.
Yes.
Yeah, you have a spaceship. So, like, if you need to travel a long distance, let's say for another like galaxy, in normal way, if you try to travel, it takes a long time. So they found another approach. So you are just shifting to another dimension. In that dimension, you are just walking, just moving a small distance, and you can directly appear in here. So if you try to go in our normal spatial domain, spatial domain, in our class also, we have this F, simple F, that is spatial. Spatial in time and space.
Yes.
Time and, because right now what we use, time and space. And our other domain, capital F, that is frequency. It doesn't have time, it doesn't have frequency, it doesn't have a time, and doesn't have a space. And the Fourier domain, it has only frequencies. Likewise, in right now we are living in a spatial domain, and in that movie they are just shifting their spaceship into the another they call mushroom network, some different like Fourier kind of a dimension, parallel world. So from there, they're just shifting it a little bit. So on the other side, they can appear. So the whole idea is you are just doing a little work to travel a long distance. So in the Fourier also.
Okay, I think I got a good. Yeah. Okay.
Yeah, whole concept is why we need the convolution. For example, if you need to take a derivative of an image, let's say you have very big image, you need to take the first derivative of the image. So it's like every pixel you need to calculate it, right? But what you can do is, no need to calculate the whole image. You can apply the derivative only to the filter. That is enough. Then you can just use a convolution to apply this filter.
Okay. Got it.
Yeah. I will explain when we come to that part. But that's the thing, so to make the life easier. Yeah. So in this one you understood, right? Take
Yes.
and symmetrize this. Then take the dot product. Okay. Yeah. This is done. Okay, we will directly jump into the other one. Okay, so I will just go to the book also. So you guys remember this one? The Fourier of this, it is a sin C function square. Hello. Yeah. So this is, if you take the Fourier, it's a sin C function. It's like this.
Okay.
Yeah, and sin C function, that is the one I drew it in here. Right now we discuss all the sin C functions. See, this is a sin C function. So like this is, like, interpolation is nothing but we will mix our function with another to recreate our original one. So I need to explain interpolation now before go deeper. I think was in interpolation. I will explain this and come. Okay. First of all, I will explain why you need interpolation. In our computers, can we store continuous values? No, because the thing is, our computers are digital. It's not analog. In analog, let's say, for example, forget about images. Let's capture some audio from a microphone. If you have a microphone, if you capture the audio, it's analog. All the signals you can see, like it's like varying every decimal places. All the waves going up and down. But when you convert this into digital, you cannot save it like that. So you need to, on the sample interval, you need to capture the value. And it's a different color. Like a sample place, I need to get the average value and store it. Oh my goodness, was okay. So let's say this place, I will just take the average value and I'll store. And I cannot just take like different sizes. It should be sample interval. Like I will just divide this into like sample intervals. Like this is why in the MP3 we have this 128-bit and 32-bit and like that. When you take this 32-bit, you know this, right? In the MP3 we have 128
yes.
bit, 256, and best is 320, right?
Yeah.
And 64-bit. When you take 64-bit, what happens is you are taking very big sample intervals like this. And when you average it, you can see a lot of things getting cut down, right? It's not a perfect one. So all of these changes you are losing when you take the average of this. So you will get something like this, the flat thing. But when you increase the sample interval, like 320, you can see you are still averaging, but the changes of that, it's very less, right? But all the average values you can store in your computer. So because we work in ones and zeros, so we need to have, we cannot keep the continuous values. So the continuous values, it's not working in our computer. So we need to use the discrete. Okay, this is why the Fourier also, like I can jump back to that. Fourier also has Fourier continuous and Fourier discrete. Practically, we observe things in Fourier continuous in with the information, and while storing, we need to store in Fourier discrete like this sigma terms. Sigma terms is in discrete, and this is the continuous. Yeah, okay. So when you take this, like I told you, like let's say our image, we take the discrete values. So we record the values. We don't have this continuous one. Okay, let's say we have these samples on the sample intervals, discrete values, and when we try to recreate the image, can we get some curve like this? And these ups and downs, can we get it? Like these shapes? We cannot get it, right? We can maximum do is we can just take the average of that. So it will not create a perfect image. It's not a smooth image. So it will not create like this. It cannot create this shape. It can just take value like this, flat value. So if we combine this with a different function, then we can recreate this. So some function like should be like this. We understood that now we need to get these curves back. So get the curves. So if we mix with the some function with the curve, we can get it back, right? So that's why, that's why we mix it this with this sin c function. What we will do for every position, every position in here, every position we will inject the sin c function. So when we inject the sin c function, what happens is, so it will be like this. And here also sin c function will come. And it will come like this. And you may ask what happens to this part. The thing is, the beauty of sin c function, it goes these corners on these positions. Is 2 pi by 8 positions. So like when you assign the function, it should go like this. So for while calculating the average, there is no impact. On the second function, when you take it, it goes like here. So when you take these averages, I mean, when you get the value from here, there is no impact from the other function, because sin c function, it doesn't go and get 0. It will continue. But there is no issue with that. You got it? Or not? Kiran, maybe you understood?
Yes, I got the idea.
Okay,
But when you told me about that side, okay, when the whole
Yeah.
function we can understand, but
No, in
it's
the sine C, the thing is, it doesn't stop from here. It will continue like this. So the thing is, when you assign sine C function into here, it assign like this, and it will continue. But in the second position also, when you assign, let's say that I assign into here, so it will go by 0. It will directly go by 0 here.
yeah, yes.
Yeah, every position, every these positions, and here there will be another function. You have the value of the assigned function only, but
Yeah.
for the reflection from the other function, there is no reflection because it becomes 0 in this position. Yeah, it goes from the 0 axis. So
Oh, okay, okay.
Yeah. So that's why, you know, it says there is no rippling effect. So they say it's like that. But the thing is, I'll go back to that lecture note again. So in this is sine C function. Likewise, sine C function, we have another one. Basing function.
Basing.
Yeah.
Yeah, basic. Yeah, what is that?
Yeah. So you can see the red color one is sine C function. Every these positions, cosine position, I mean, this pi 2 pi by 8 position, I mean pi by 8 positions. I don't know what is correct because in one place it's mentioned 2 pi by 8. In here it's mentioned pi by 8. In above you can see it's 2 pi by 8. We need to ask from him. So so every these position, pi by 8 positions, it is 0. But in the basing function, it's not like that. It's not going to the exact positions. So when you apply for the second position, because now this interpolation function, you need to apply to every what do you call this? Every discrete values you need to apply.
Every discrete values, yeah.
Yeah, you need to apply on every position. So because of this rippling effect, when you create the image, you will get some distortions like you can see rings around this.
Yes.
Yeah.
Yeah, you
Yeah.
get these rings because of that. Because in sine C, when you apply, you saw it exactly what happened. There is no effect. It exactly becomes 0. But on the second position also it becomes 0. There is no effect from the other function. See, it's 0.
Yeah.
But in the basing function,
Okay.
if you apply, it's going like this, crossing.
Yes.
Yeah, so this one has something, it's crossing. So when you take the sum value in here, it's not this. You get something bigger. So that is not what you calculated, right? So that's why you are getting this rippling effect on basing function. So it is not perfect. And why we cannot use sine C? The thing is, it's made from a square. So in the Fourier domain, it's actually not distributing through all. I mean, it's not even. Like you can see by some axes, the power is more. Some axes, its effect is low. So that's why combination of both of these, we need to go with Gaussian. Gaussian, you know, if you apply Gaussian in one axis, I mean, it's like this. But let's say, for example, I need to apply on the other direction also. Like 2D, this is in 1D. In 1D network, if it is like this, if it is 2D, we get the highest point here. Something like this. Like we'll see one.
So then you're saying that to these discrete functions, you cannot apply sync or basing function. Is that right?
We can apply, but you know, the thing is, you know,
For
we don't
to interpolate, yeah.
Yeah, we can use sync and basing as interpolation function. We can use, but there are some distortions with that. If
Okay.
yeah, so it's not perfect.
So that's why we're trying to use Gaussian here.
Gaussian, yes. Two dimension what we need. Let's try to find some images of that. Yeah, like this. So we will apply something like this. But the thing is,
Oh, okay.
yeah, it doesn't go to 0 because based on theory, it doesn't go to 0, right?
Yeah, this is
Yeah.
actually a 2D Gaussian, right?
2D
That's
Gaussian.
what you're saying.
Yeah.
Okay.
So when we apply the Gaussian into these positions, and we need to reduce the because the only control factor Gaussian to reduce this curve into something like a very small one or very bigger one, we can adjust by rho, standard deviation. So only our modification, I mean our what we have the control over Gaussian like standard deviation. So we will apply Gaussian in here, and we will apply Gaussian in here. Like that, we will apply the Gaussians. Okay. This is the actual summary. This is what we will do. But if we apply the sin c function in here, I need to show the equation. So this is the equation that this is in 615 from the book. Even I will show you. 615. We are in 8.
That is the Gaussian or the sinc function?
This is sin function, but we can use anything. But the equation is same. 15. Yeah, this is the one. Actually, how they got this? They assign sigma from above. I believe from here. So construction is no need. If you know the concept, that's enough.
Is this something related to that convolution that you said? Because
Yeah.
we are shifting it.
Like it's like a not exactly, but this is how you reconstruct the image, because when you store these discrete values, this is how we reconstruct the image. But right, I mean, still we didn't discuss about the recreation part, because in this theory they put in the Fourier domain. So the reconstruction, we are not going to the Fourier. You can see the small f in here, and this is your original discrete values, and this is your interpolation function. So we will not take the Fourier to recreate the image. When you have this discrete value, you can directly can take the what do you call it, interpolation function, and you can recreate the image. But this equation in 815, it's like it's both same, but they use different letters because the above one it's proven in the Fourier domain. Then only we took it into here. But the thing is, you apply every position your interpolation function, then you are increasing the magnitude of that function, but by this value. That means, let's say this value is like 1, and here the value is 1.2, like here the value is 1.3. We are multiplying by that factor. So in here you can see this is the height of the function, this is the height is increased, and this is height is like this. You can see the scale exactly. This is like 2 pixel in my book. So this is height is 2 pixel, and here it's 4 pixel in the middle one. See exactly the same height. See, likewise, you are increasing the height. It doesn't matter what function you apply, you need to do the same thing. You have 3 options: sin c, Bessing, and Gaussian. Why we apply Gaussian? Because it doesn't have much issues like other two. Also, one more important thing is there, the computations. Let's see. I don't have the okay. I need to send one photo into here. Guys, just wait a minute. I need to test 2 photos into here.
Okay.
Also, we didn't discuss how when the convolution happens, how the size is changing. Just a minute. I'll just mute myself for 1 second.
Hello, Kiran. On
Yeah.
online. Okay, I have some connection issue. I don't know. Just checking. Okay.
No, I just mute myself. Just a minute. I need to copy this image.
No problem.
I thought I copied everything, but did I copy 2 or 1? Copy only 1. So we'll start with this. Maybe you ask how this filter is applied and how the output size is
Yeah.
changing. So actually, when you do the convolution, what happens is your filter should start from here. Like you can see, my original image is 5 by 5, and filter is 3 by 3. See, it should enter from here, this direction, like this, 3 by 3. And the second position, it should be like this, and third position should be like this, and fourth should be like this. And this is, I just constructed some middle scenario. So you can see this is your first, you will do convolution like this, and second like this, like that. But how many convolutions there on this direction? You can see 7. 1, 2, 3, 4, 5, 6, 7. And down also, if you do it, like it will be the same, right? Yeah. So that's why your output image is 7 by 7. And how to calculate this? You can see, just this size, I mean this image size, and add 1 minus this size, like 3 minus 1.
Okay. 5 plus 3 minus 1.
Yeah. So if you, this is the shortcut way to do it. Yeah. And also one more thing.
Got it.
Yeah. One more thing I forgot to tell you. Like this is how you do the convolution. And you can do one more thing. I mean, like how many steps, how many computations you need to do in here. So in this direction, we need to do convolutions 7 times. And down
7,
direction,
yeah.
we need to do 7 times. That's been 49
49 times.
times you need to. But the thing is, if you just take the image, original image, and convert that image into Fourier domain, and your filter also convert into Fourier domain, and just do pointers multiplication. Just close my window. Some sounds. Yeah. So what you will do in the Fourier domain, you just take this image, and this one also you just take it and convert into Fourier, and just do pointwise multiplication. But the thing is, these are in two sizes. You cannot do pointwise multiplication. Pointwise multiplication in the sense, this point you need to multiply with this. But in that case, what happens to these points? So what you will do, you will artificially create like this. So the zeros comes around that, this 3x3 filter. Now you can multiply this one with this one in the Fourier domain. Okay. Then when you multiply, how many multiplications you are doing? Here it's 49. In there it is 5 by 5. Only 25 times. So you, yeah. If the image is bigger, you can do a big cost saving, right? This is for a small one. So that's why I told you, like in the Fourier domain, you are making your life easier. Whatever you do, the things in Fourier domain, it's less calculations. We have the shortcuts. So we can just check that lab also. We applied one filter. Which lab was that? And anybody remember? I think this one. Part one. Maybe part 2. Let's see. This is, I will explain. The part 3. Okay, I believe this is the one. So you have this 3x3. That's the 5x5 original one, and this is 3x3 filter, second one, and you get, when you convert, you get this last image. This is figure 1, I believe. Figure 1, you can see. Yeah. So you have your F, original F, it is 5x5, and second one G, your filter. So it is 3x3. When you take the convolution, you get Y. Okay, you get this one. So now we will do the same thing on the Fourier domain, and you just convert into Fourier, and second one also. This is when you original filter size is 3x3, but when you give this, it artificially adds zeros around that and calculate the Fourier. But when you calculate the Fourier, there is no zeros around that anymore. Inside this, yes, it will assign zeros like how I explain in my book, like this. This is how you put the additional zeros. But when you take the value, there is no zeros anymore. Because in the Fourier domain, it's a conversion. So I can just take my G and show you. See, there is no zeros in any place. Got it? Yeah. Okay.
Okay.
Yeah. So what you will do, pointwise multiplication. This is very, I mean, this is a simple for pointwise multiplication. That's mean you are just multiplying first point with the first point, second point with the second point, like that. Understood, right?
So, again, so on the, to get G, you're just doing the Fourier transform and giving the size 5x5 automatically. You put the values.
So this one even no need to give, because the original one itself, it was 5x5.
Yeah, that is 5. But for
Yeah.
G, we are making from 3 to 5, right?
Yeah, because in the point we need, I mean, end of the day, what we need to do is pointwise multiplication. But
Yes.
to do the pointwise multiplication, the sizes should match. So
Yes.
we artificially expand it. So that is what we do.
So my point was, if you just give the FFT2 function and give the size, it will automatically give you that size matrix.
Exactly. It will do the things.
Okay, it's part of the function. Okay.
Yeah, part of the function. So in here, first position will multiply with the first, and second position with the second, and third one with the third. Oh, my scale is wrong, but you got the point, right?
Yes.
Yeah. So then when you like just print the value, I believe YY is the last one in the second row. It's not the same. It's not the same like above. it's a like good calculation. You don't get this weird border, but it's not the same. So if you need to get the same, what you need to do is you can see like in here in the calculation, we saw when you like the spatial domain, then normally when you apply convolution filter, it increase the size. You get a 7 by 7 image. But you tell me what's the size of this image?
5 by 5.
5 by 5. So the thing is, the secret is in the Fourier domain also, we will create the image by forcing it to become 7 by 7. If you know how to get the 7, when we force it, then when you do the calculation, you will get exactly the same image. Sorry, not this. See, exactly the same one, like above. But number of calculations, it's less. The previous one actually, it's previously when you apply this filter, every pixel not 49 exactly. It's wrong actually. It's not 49. Every pixel you need to like the original image. I made a mistake previously. Original image was 5 by 5, and this is 3 by 3. So every pixel when you can like convolute, you need to do 3 by 3 calculations. So every pixel you are going to do 9 calculation into your image size. So the whole calculation, it's like image size is 5 by 5 in 3 by 3. So this many calculations, like 25 into 9. So what's the value? 225? I believe 225, right?
Yeah.
In here, now we scale the image into 7 by 7, both of these, and we are doing pointwise multiplication. So it's same like the size of the image, right? 7 by 7. We are doing 7 by 7 calculations. So it's 49. Let me double check. Like it's 7 by 7. Same size like the image, every pixel. It's pointwise multiplication. Yeah, it's 49. So we did a very big cost saving. In here, actually, this is the correct one because every pixel we are doing 9 calculations.
Yeah.
Like this filter size. Yeah. And also there is a command in MATLAB. If you need to get the original one in also into the original size, there's a command called same. You can force it actually. There's a small command when you convolute, can just give like this same. So what this will do, it will create the original one also into the same size.
Okay.
Yeah, output one. You can see.
So it will be 5 by 5.
Yeah, we can print the size of size Y. No, I think I gave in the wrong way. Same should be inside. Yeah, you can see 5 by 5. 5 by 5 came, and here also border it's changed now. Yeah, just because it came on the questions I saw. So this is the way if you need to get post from 7 by 5. Okay. So we will go back to our next okay, this one also I'll explain. This is nothing but this is this is a circle. When you take a Fourier transform of a circle, what's the value you should get? It's a sine C. No, it's sine C. No, it's a basing, right? Yeah. So this is the basing, and that is a Fourier transformation of a circle. So what we did, we took a basing of this, and when you increase the size, what should happen? Now you increase the alpha. On the other domain, it should reduce. Okay, the rule.
Yeah. The property, yeah.
Yeah. So rule is this here, exactly this one. We are multiplying with alpha. Now we are not increasing, we are reducing. In the other domain, what should happen? Then in the other domain, it should become. No, we increase it. if we make it in this domain, if we increase, other domain it should shrink.
Decrease, yeah.
So this is the same thing happens. In this domain we increase, and this domain, Fourier domain, it reduces size. Yeah, this is the proof of that. Okay, let's see. Yeah, okay. So we'll go to the next one. Convolution. What about others? Is it clear?
Yes, Gayan, it's clear.
Okay. Yeah.
Yes, it's clear.
Okay. On the basic, the Gaussian, the thing is in the there is something called separable. I will come to that property also. Separability. Separability I can explain by I had a small diagram. Okay. Filters. Now, when we apply these filters, let's say it's convolution. You know how the calculation is done. So if our original image is like 5 by 5, 5 by 5. So let's draw a small 5 by 5. 1, 2, 3, 4, 5. In this direction also 1, 2, 3, 4, 5. So this is our original image. When we apply this filter, we know every pixel we need to do 4 by 4 calculations. Then for the whole image, we need to apply this. That is 5 by 5. What's the amount we will get? 25 into 16. We need to do 400 calculations in this way. Okay. Let's say, for example, a moment, I mean, we don't need to go for the Fourier domain. We are trying to optimize it in the frequency domain itself. So what we can do is, if it is possible to separate this filter into this somehow. So that somehow also I can explain, but we will just say it for somehow. So yeah, first I will explain how this is done. Let's say, for example, you can you have these two vectors on this direction, and we are doing some dot product of these two. Okay, if you have values 1, 2, 3, 4 here, 1, 2, 3, 4 here, what's the value you should get? You should mesh these two, and for the other side, you will get the output. So you will get a 4 by 4 matrix. Is it understood?
Yeah, 4:1 into 1:4.
Yeah.
Here the columns, here the rows should match. Then you should get the other directions 4 by 4. So you will first multiply 1 with 1, 1 with 2, 1 with 1, 1 with 2, 1 with 3, 1 with 4. You get 1, 1, 2, 3, 4 here. And here you should get 2, 4,
2, 4,
6, 8.
6, 8.
Yeah,
3,
here should 3, 6,
9, 12.
9, 12. And last you will get 4, 8,
4, 8, 12,
12,
16.
16. Okay. Let's say you have your filter this. If this is your filter, given filter, you can separate it to column and row vector like this. But not everything, because if I just put the random numbers, no, you cannot separate it. So this is a separable filter. So that's the meaning of separable filter. Okay. So if you have it, now we'll do the calculation. We'll apply this filter first. So your filter size is 3, and you are multiplying with this is 5 by 5. Okay. And for that results, you are I mean, what's the size of your results? It's the same size, right? When you will get the same size image. So for that one, you are doing the calculation again for the second filter. So it's a 3 filter into 5 by 5. How many calculations? 25 into 3, 75. Sorry, my filter is not 3. My filter is 4. My filter is.
Okay. Yeah.
So this is 100. This is 100. Earlier we got 400, right? Now we got only 200. So our calculations are very less, right?
Yes.
If the images are bigger, like in megapixel, million pixels, so there is a big difference. with this way if you have separable filters. So that's
This is the only case if you have separable filters.
Yes. And the thing is, now what are the filters in okay, we'll go back. Interpolation, what are the filters we have? Because you saw interpolation is also kind of a like convolution. Okay, interpolation. In the interpolation also, we need to apply filters. Now, if it is separable, we know our calculations are less. But the thing is, sin C is separable because sin C equal sin theta divided by theta. So sin t is one part, theta is one part, so it's separable. And the Bessing function is not separable. And the Gaussian, 2D Gaussian, it's separable. 2D Gaussian, I can just take his lab guide. Which lab we did that? Can anybody remember? Gaussian filters. Oh yeah, this one exactly. See, now we have filter like this. Actually, this filter is constructed. If you have two 1D filters, always to make 2D Gaussian, we need to multiply two 1D Gaussians and we can make it. This is the only way we can make it. So always we can 2D Gaussian, Mexican hat, we can separate it to two 1D Gaussians. Got it? Got it, right? So there is no other way we can construct it directly. We construct it directly like how I construct that matrix. I just multiply two vectors, right? Likewise, this is constructed by multiplying two Gaussians. So this is always separable into two Gaussians. So what we will do, we apply one Gaussian first, then for the result, we will apply the second one. Okay. So in the commands also, like with the first filter, we'll do a convolution with the first filter. Then for the result, we'll for this result, we will apply the second filter. Got it? Yeah. Here we apply the first filter, first Gaussian. So this is your original function, and this is your Gaussian Ex. And let's say this result is y. Now for this value, we are applying the like this is your now resulting value. We are applying the second filter. We don't apply it one time. If you apply it one time, your computations are high. And in both ways, if you do, your result is same. This is lab 4. We'll open it and see. You guys need a break? Or shall I continue?
Yeah. Again, why are you doing it twice? Convoluting it twice?
No, because actually what we need to do is we need to apply our original image is 2D. So we need to apply 2D filter every position. So that is the whole purpose.
Okay.
Original image is 2D. So, but we need to apply 2D filter for every position, like moving filter.
Two
like
Gaussian, yeah, okay.
But the thing is, if we apply it, we saw the computations are very high. But the thing is, we can get the same result by applying two 1D filters. Two 1D filters. If you do that,
that's why I did twice. Okay.
Yeah. In here, you can see he constructed the 2D filter in one shot, because in the based on map we can do it. Like this is the exponential function, so these two terms will get add to each other. So we can construct it in the last part in one shot. So that is what he did. This is directly a 2D filter, and this is he just normalized it, and it's printed in here 2.21. That's when it's the first one. But we don't need that. I need to see the answer with that. Okay, then again he created the second filter, individual filter. You can see this is a 1D filter. It's not a 2D filter, it's a 1D filter. and his x and y both are same. He just make a copy to the y, but in the other direction orthogonal. Okay, because one should be in this direction and other should be in the other direction, row and column. So that is why he used this. He didn't use two functions for this. He just used the same one, gx only, but he just transposed it. Okay, now we will apply this into the images. I believe it is in part 2. Okay. Now this is our first filter, and GG in the sense when it is not important. One more thing, this 2D filter, you can mathematically, you can compute and then create. Otherwise, you can create 1D and just do convolution with the same, like with the other one. Then you can make the it's the same answer. This is what he did. Like in here, he made the 2D filter with one line based on this math, based on this. Then in here, we just use the convolution of your 1D filter. Then you make the 2D filter. These both are same. That is what. And when you print it, I believe the answer should be the same. See, it's the same. But it's not the important one. The important one is, okay, for our image, we are just reading an image. For that image, we are applying a 2D filter. That is one thing. Then we should apply the filter separately. Yeah. Yeah. Here, what we did, this is the fourth. Yeah, applying GG. Yeah, this is when we apply 2D filter. Apply 2D filter GG. And this is the same one. We apply the first 1D filter, then we apply another filter. This is 2 into 1D. You can see both of these images are exactly same.
Yeah.
It's like we create little blur image, but blurriness, because it's the same. It's the same. Yeah, that's the whole purpose. You can, if it is separable, you can cut down the cost. The fourth part of the lab, the third part. Okay, yeah, this is another thing. If you have the noise, we saw like like first one itself we saw. If we have the noise, even it couldn't recognize that voice I. First lab we introduced the noise and it couldn't recognize.
Yeah.
Yeah. So just a minute, I got a message. Yeah. So what we can do is to fix these issues, we can apply some filter, then it will reduce the noise. But the thing is, if you in the class, what we did, we apply a bigger filter. But if you apply a bigger filter, image also get blurred. But you can see the image is blurred, but still, when you compute the error between this one and the original image, error is high on this. See, this is we calculate the error.
Okay.
With the we calculate the norm of the original image without doing anything the original image, and we compare the norm with the noise image. So we get a higher value, even though the value is the image is blur on the second one. When we compute the norm, it is lower. So yeah, in the computers, noise is far more worse than blur. See, this is a blur image. When you compute the error, how we compute the error? We took the norm of the original image. We calculate the f of the norm of the original image, and we minus the norm of the blur image. This is what we did. But this is better than the noise. This is the noise image. But you can see if I just reduce, change the size of this G into a little bit lower, because our filter is too big. But if I reduce the size of the filter, you will get a perfect image. So like this is little blur, but if I can change it, this is I think noise. I apply this filter G1. But let's see if I can reduce. This is 2.4. Let's see. Yeah, you can see now this image is like perfect, right? So this is the original one. And by the way, you know, something wrong with my code. You saw previously this image was blur. Now when I change it, it's modified both of these places. But you can see like we can recreate the image by introducing a little filter, little blurriness. So it's a low pass filter. By introducing a small low pass filter, we can recreate the perfect image. So then we can start do the computations.
Yeah. But
So let's move on. I believe, what is this? I believe we can do this. Yeah, derivative of the image. Okay, this is the important one. So I'll just jump in and I'll directly explain. When you take the derivative of the image, we are taking it on two axes in here, x and y. Derivative, you know, like when you take the first derivative, we can identify the highest and lowest points. That means highest and lowest changes. So if my graph is like this, so this is the highest peak. So it can identify, I mean, first derivative of here, it's 0. So, and if there is another one, I can identify the points. So here also, so these are the maximum change. So for example, in here, this is the maximum change. And if it is unified color, there is no changes. So likewise, when you apply the first derivative, these are the crossing points, something like here, you will get the highest acceleration. For example, if this is a curve, where do you get the highest acceleration in here? Maximum changes, right? So when you have the distance, when you take the first derivative, you get speed. Then when you take the second derivation, you get the acceleration. Likewise, if this is your vector, when you take the first derivation, you get the maximum changes. So you will get the maximum changes in here, these edges. Okay. When like there's a black to white, it's a biggest change, right? So this border, it should come in white color in that case, because highest value represented by the highest color, right? Let's say our scale is between 255 to 0. So the maximum change, it should represent by the highest value. So that's why you can see in these borders, it came white color. And when you leave from that, you get the lowest. So the graph lowest acceleration, like in here, something like here. So when you leave from white to black, you get the lowest point. So that's why you get black points in the black marks in here. Got it? Yeah. So in the other one also, when we approach from here,
other axis.
Yeah. So black to white, you get the highest. So you should get white. So that's why you are getting white in here. But when we leave that point into here, so white to dark, so that's it's like, you know, stepping down from this mountain. So you will get these kind of points. So these are the negative, highest negative points. So it represents by 0. So that's been black. That's why you are getting black in here. And there's one image I saw when we combine both of these. There was one combined image, right?
Yeah. Then we'll have all that.
Yeah. So it's a noise image, by the way. But you can see, like we check from both directions. That's why we get this white border. But if there is no noise, you get nice board actually. We can. Okay, I will Can you see where I introduce noise into here? M noise. Okay, we'll just, for a moment, I will just cancel out this. Yeah, I will just cancel out this line. So now without M noise. Oh, no, I need to cancel out. I will do it properly. Yeah. Now without noise. See, you can see the border. So, so let's go back to the original discussion in here. Do you remember this image? Yeah, this one. So if we if we take the first derivative of this car image, so we get the borders, and then if we apply this filter, so it will be more more effective, right? In that case.
Yeah. Okay.
Yeah, because it's like in this way, you know, a lot of changes there. But we can make easy filters because we will have only black and white, and we'll get all the borders if we apply if we take the first derivative of the image. It's right. So it's an easy thing, right?
Yeah.
In the use case.
Yeah, better than original image.
Exactly. So yeah, this is just one idea came to my mind. I don't know, like maybe that is how they are doing. So I'll just remove my noise filter also. And one more thing, I mean, this is like okay, so our Gaussian filter is like this. So what if we take the first derivative of this filter? So if we take the first derivative, this is uphill, right? Uphill in the sense you should get something like no, something like this, I believe. Because in here the middle part acceleration is high, lower part it's low, so you should get something like this. And when you go on the top, you should get your acceleration again becomes zero.
Becomes zero.
Yeah. And when you go down, what happens? All the acceleration values, it should be inverted, right? So you should get something like this.
Okay.
When you take the first derivative of your Gaussian filter. Okay. Then, but when we print in the lab, we got something like this. Can anybody explain me? The thing is, I believe we took the absolute of that.
Yeah, we are squaring it.
Yeah, see, we took the absolute. When you took the absolute, there is no minus values. We are just pushing it up.
Okay.
Again, we don't have absolute in L1 norm, right? We don't have any minus value. We are converting minus into plus. So that's why we get something like this. But I don't know whether it's possible or not. Because if it's complex numbers, yeah, see, we got the part goes down. It doesn't come in perfect way because I believe in the complex numbers we have this. This is because the imaginary part we cannot display. So otherwise we should get what I drew. But main idea is why you get the image like this, both up. It's because we took the absolute.
Okay.